We exist within a narrow sliver of reality, a thin veneer of light and matter that we have mistaken for the whole of existence. Since the dawn of our species, we have looked at the stars and assumed that what we see represents the sum of all things. We cataloged the galaxies, mapped the constellations, and built a physics based on the tangible, the things we can touch, measure, and ignite. Yet, as our instruments have grown more sensitive and our mathematical models more precise, we've encountered a chilling realization. The universe does not behave as if the stars are its primary inhabitants. Instead, the cosmos moves as if it is being steered by a colossal, invisible hand, a ghost in the machine that outweighs everything we know by a staggering margin. We are like travelers standing on a dark shore, watching the foam of distant waves while remaining entirely blind to the vast cold ocean that moves them. This is the central crisis of modern cosmology. If our current understanding of gravity is correct, then everything we have ever observed, every atom in every star, and every cell in every human body, is merely a dusting of cosmic debris floating on a sea of something else. To understand how much of the universe is actually made of dark matter is to confront the possibility that we are the exception, not the rule. To find the answer, we must look past the light and into the shadows that hold the stars in place. For most of recorded history, humanity has lived by a simple assumption that to see a thing is to know it. The eye, we believed, was the arbiter of truth. What shone could be measured. What glowed could be weighed. Light was not merely a messenger, it was the message itself, carrying with it the essence of matter, the signature of mass, the proof of presence. This faith was not unfounded, built empires of understanding. From the flicker of candlelight reflecting off a balanced scale to the refraction of starlight through a lens, the visible world offered itself up for interpretation. The great minds of the Enlightenment operated under a covenant with brightness, that the universe, in its generosity, had made itself known through illumination. To chart the heavens was to catalog light, to understand matter was to observe its glow. The stars cooperated beautifully with this arrangement. They burned with predictable rhythms, traced orderly paths, and congregated in elegant spirals and clusters that seemed to obey the same laws that governed. Falling apples and swinging pendulums. When astronomers turned their instruments toward the great island universes, faint smudges of light that would later be called galaxies, they expected confirmation, not contradiction. What they found instead was motion that made no sense. In the early 20th century, as telescopes grew more powerful and photographic plates more sensitive, astronomers began to study not just the positions of galaxies but their speeds. They measured the rotation of spiral nebulae, tracking how quickly stars orbited around galactic centers. They observed the velocities of galaxies within clusters, noting how these cosmic cities moved relative to one another. The mathematics were straightforward. Gravity, after all, was a solved problem. Newton had given us the equations. Einstein had refined them. The mass you could see should produce the gravity you could measure, but the numbers refused to reconcile. Stars at the outer edges of galaxies were moving too quickly, far too quickly. According to the visible mass tally of all the light-emitting matter, all the stars and glowing gas clouds, these outer regions should have been moving sluggishly, their orbits lazy and slow. Instead, they whipped around galactic centers at speeds that defied the gravitational pull of everything that could be seen. By all rights, they should have been flung into the darkness of intergalactic space, cast off like stones from a spinning wheel, yet they were not. They held their positions. They maintained their orbits with a stubbornness that suggested the presence of something else, something that exerted gravitational influence without announcing itself through light. The initial reaction was not alarm, but puzzlement. Perhaps the measurements were wrong. Perhaps the instruments needed calibration. Perhaps there was dust, or gas, or some population of dim stars that had been overlooked. Astronomers checked their work, refined their techniques, and measured again. The discrepancy remained. In some galaxies, the visible matter accounted for only a fraction, sometimes as little as 10% of the gravitational mass required to explain what was observed. This was not a small error. This was not the sort of rounding difference that could be dismissed with a footnote. This was a chasm between what was seen and what must be true. The galaxy clusters posed an even more profound problem. When astronomers measured the speeds at which galaxies moved within these vast congregations, they found velocities so high that the clusters should have torn themselves apart billions of years ago. The visible galaxies, brilliant as they were, did not possess enough combined mass to hold the cluster together. And yet the clusters persisted, stable and ancient, as if bound by invisible hands. Fritz Zwicky, working in the 1930s, was among the first to confront this mystery head-on. He studied the Coma Cluster, a sprawling assembly of over 1,000 galaxies, and calculated the mass needed to keep it gravitationally bound. The result was staggering. The cluster required nearly 400 times more mass than could be accounted for by its visible light. Zwicky proposed that the missing mass must be present but unsend dark matter. He called it, in a term that was both descriptive and unsettling. The idea was largely ignored. It was too strange, too inconvenient. Surely there was a simpler explanation. Surely the universe had not hidden the majority of its substance from view. But as decades passed and observations accumulated, the pattern became undeniable. Every rotating galaxy, every bound cluster, every large-scale structure told the same story. The light was lying. The luminous matter, the stars, the nebulae, the radiant dust was not the foundation of cosmic architecture. It was decoration, a veneer. The universe had built itself on a scaffold that did not shine. This realization arrived slowly, not as a sudden revelation, but as a creeping acknowledgement. The visible universe, it turned out, was only a tracer. The stars and galaxies were markers, breadcrumbs scattered across a much larger landscape. They outlined the presence of something deeper, something that shaped the flow of matter and the curvature of space without ever interacting with the electromagnetic spectrum. The cosmos had mass that bore no relationship to brightness. What emerged was a picture of profound humility. Our eyes, tuned to the narrow band of visible light, could perceive only a small fraction of what existed. The telescopes that extended our vision into infrared and ultraviolet, into radio waves and X-rays, still captured only the luminous. They were instruments of light, and light, it seemed, was the minority report. The universe had not made itself entirely knowable through illumination. It had kept something back, something vast, something that comprised the majority of its mass and shaped the destiny of every star and galaxy, yet remained stubbornly, completely invisible. This missing mass was not an error in accounting. It was not a gap to be filled by better telescopes or more careful observation. It was a fundamental feature of reality. The universe, in its construction, had chosen to build most of itself from substance that would never glow, never heat, never emit or absorb light in any form we could detect. Our assumption that to see is to know had been quietly, definitively overturned. The implications of this discovery rippled outward in ways both practical and philosophical. If the majority of the universe's mass was invisible, then every measurement, every model, every confident assertion about cosmic structure had to be revisited. The maps we had drawn were incomplete. The census we had taken had missed the majority of the population. We had been describing the architecture of the cosmos while seeing only the windows, not the walls. Astronomers began to approach their work differently. The question was no longer simply where the stars were, but where the darkness congregated. If galaxies rotated too quickly, the invisible mass must be distributed in a particular way, concentrated at the center with the visible matter, but spread in vast halos extending far beyond the visible disk. These dark halos, it seemed, were the true bodies of galaxies. The spiral arms and glowing cores we photographed were merely the bright nuclei of much larger, darker structures. Computer simulations confirmed the necessity of this arrangement. When scientists modeled galaxy formation using only visible matter, the results were chaotic and short-lived. The simulated galaxies flew apart or collapsed into unrealistic configurations. But when dark matter was added distributed in specific patterns around and through the visible components, the simulations produced structures that looked remarkably like the real universe. Stable spirals, elliptical galaxies, clusters that endured for billions of years. The dark matter was not an addendum to cosmic structure. It was the foundation, the scaffolding, the framework upon which everything luminous was built. This framework revealed itself through subtle signatures. Gravitational lensing, predicted by Einstein's general relativity, became a tool for mapping the invisible. When light from distant galaxies passed through regions of space containing massive concentrations of dark matter, the light bent and distorted, creating arcs and multiple images of the background sources. By studying these distortions, astronomers could infer the distribution of mass along the line of sight-even mass that emitted no light. These lensing studies painted a picture of a universe laced with dark filaments and nodes. The dark matter was not uniformly spread, but organized into a cosmic web, with dense intersections where galaxy clusters formed and tenuous strands connecting them across hundreds of millions of light-years. The visible galaxies, it turned out, traced this web like pearls on invisible strings. The arrangement suggested a history. In the early universe, when matter was still nearly uniform, dark matter must have begun clumping first, pulled together by its own gravity. These clumps grew, attracting more dark matter and creating gravitational wells deep enough to draw in ordinary matter, hydrogen and helium that would eventually ignite into stars. The first galaxies formed not in isolation, but within pre-existing dark matter halos. Settlers moving into cities that already had their foundations laid. This timeline rewrote the story of cosmic evolution. The visible universe, with all its drama and brilliance, was a late arrival. The dark matter had been organizing itself for hundreds of millions of years before the first stars lit up. The light we cherish as the signature of existence came only after the architecture was already in place. Yet for all its gravitational influence, dark matter remained stubbornly non-interactive in other ways. It did not collide with ordinary matter in any detectable fashion. It passed through planets and stars and human bodies as if they were empty space. It felt gravity and exerted gravity, but appeared immune to every other force. No electromagnetic interaction, no nuclear binding. It was present but intangible, influential but unreachable. This ghost-like quality made dark matter maddeningly difficult to study directly. Every attempt to detect individual dark matter particles efforts involving underground detectors, satellite observatories, and particle colliders yielded ambiguous results at best. The particles, if they existed, were extraordinarily elusive. They might be passing through the Earth in vast numbers at every moment, trillions streaming through every square centimeter, yet leaving no mark, no ionization trail, no measurable disturbance. The search for dark matter became an exercise in inference and elimination. Scientists knew what it was, ordinary matter made of protons and neutrons would interact with light and would have shown up in surveys. They knew what it could U and B. Compact dark objects like black holes or dim stars would produce detectable gravitational effects and would have been observed. Through microlensing studies, what remained were exotic possibilities particles predicted by extensions of the standard model of particle physics. Entities with properties unlike anything yet confirmed in laboratory experiments. The leading candidates had names that sounded more like poetry than physics. WIMPs weakly interacting massive particles. Axions, sterile neutrinos. Each represented a different solution to the puzzle, a different way that matter might exist without shining. Each remained hypothetical, supported by theoretical elegance, but lacking definitive experimental confirmation. This absence of direct detection did not diminish the certainty of dark matter's existence. The gravitational evidence was overwhelming and consistent. The rotation curves of galaxies, the velocities of cluster members, the gravitational lensing patterns, the structure of the cosmic microwave background. Every independent line of evidence pointed to the same conclusion. Most of the matter in the universe was dark, and it had been dark since the beginning. What we were left with was a profound redefinition of normalcy. The matter we are made of the protons and neutrons, the atoms and molecules. The substance of stars and planets and living things was the minority constituent. It was the exception, not the rule. The universe had composed itself primarily from something else, something that did not participate in the chemical reactions, the electromagnetic processes, the light-emitting phenomena we associate with matter. Our eyes, tuned by evolution to detect reflected sunlight, had been optimized for a rare condition. We were adapted to perceive the atypical, the normal matter of the universe, if dark matter could be called normal, was invisible to us by design, not by accident. There was no evolutionary pressure to develop senses for detecting particles that pass through biological tissue without interaction. In this light, the visible universe began to seem less like the primary text and more like marginalia. Important, certainly, rich with detail and beauty. But not the whole story, not even most of the story. The luminous galaxies were comments written in the margins of a much larger, darker manuscript. And so we arrive at a threshold of understanding marked by absence rather than presence. The universe has revealed itself to be fundamentally other than what our senses suggest. The framework that holds galaxies together, that seeds the formation of cosmic structure, that comprises the majority of gravitating mass, refuses to shine. It will not heat. It will not glow. It offers no photons, no electromagnetic signature, no visible trace of its existence. Our eyes, it turns out, have been lying to us all along. Not through malice or error, but through limitation. They showed us what they couldn't. What they could see was never more than a fraction of what is. The human mind was not designed for this kind of problem. Every structure in our brain, every neural pathway dedicated to understanding the world, was shaped by survival on a planet bathed in visible light. Our ancestors learned to read the rustle of grass, the shadow of a predator, the color of ripening fruit. They navigated by starlight and moonlight, tracked prey by footprints pressed into soil, recognized kin by the contours of familiar faces. The entire architecture of human perception was built around one fundamental assumption: that reality announces itself through interaction. Touch tells us where solid objects end and empty space begins. Sound travels through air and water, carrying information about distance and direction. Smell delivers molecules to receptors, translating chemical presence into awareness. And light above all provides the richest stream of data, millions of bits per second, painting the world in color and shape and depth. This sensory apparatus is extraordinary within its domain. The human eye can detect a single photon under ideal conditions. Our ears distinguish between thousands of frequencies. Our skin registers temperature changes of fractions of a degree. We are finely tuned instruments, calibrated by millions of years of evolution to extract meaning from the environment. But we are tuned to the middle ground of reality. The scale at which we operate, the scale of organisms measured in meters. Living for decades, moving at walking pace, occupies a narrow band between the quantum realm and the cosmic. Our intuitions were forged in this middle territory. We understand falling because we have fallen. We grasp leverage because we have lifted stones. We comprehend distance because we have walked across landscapes where horizon and destination are visible. When reality departs from this middle ground, our intuitions begin to fail. At the quantum scale, particles exist in superposition, occupying multiple states simultaneously until observed. They tunnel through barriers that should be impenetrable. They become entangled across distances, their properties linked by connections that have no classical analog. None of this aligns with human experience. We have no evolutionary precedent for understanding matter that behaves this way. Our minds rebel against it, insisting that objects must be in one place at one time, that causes must precede effects, that information cannot travel faster than light. Yet quantum mechanics is not a matter of opinion. It is confirmed by every experiment, verified by every device built on its principles. The universe operates this way, whether our intuition accepts it or not. At the cosmic scale, similar breakdowns occur. Space-time curves under the influence of mass, bending the paths of light and stretching the flow of time itself. Galaxies recede from one another not by moving through space, but by the expansion of space itself, the fabric of reality growing between them. Black holes compress matter to infinite density, creating regions where the familiar laws cease to apply and singularities form that mathematics cannot describe. Again, our biological inheritance provides no framework for grasping these phenomena. We evolved in nearly flat spacetime at velocities far below the speed of light, in gravitational fields too weak to produce noticeable distortions. Our brains never needed to model extreme curvature or relativistic speeds. The concepts remain abstract, accessible only through mathematics, never through direct sensory experience. Dark matter represents a different kind of cognitive challenge. It is not distant like a quasar or small like a quantum particle. It is here, present in vast quantities, permeating the galaxy, passing through the Earth and through our bodies at every moment. Its effects shape the very structure of the cosmos. Yet it offers us nothing to perceive. No photon to catch our eye, no pressure against our skin, no electromagnetic signature of any kind. This is not merely invisibility. Glass is invisible under certain conditions, but it still interacts with light refracting it, reflecting some wavelengths, casting shadows. Air is transparent, but we feel it when the wind blows, hear it when sound waves propagate through it. Even the neutrinos that pass through the Earth by the trillion barely interact with ordinary matter, yet occasionally one will strike an atomic nucleus, producing a detectable signal. Dark matter does none of this. It participates only in gravity, the weakest of the fundamental forces, and possibly in interactions so rare or so subtle that decades of searching have not yet confirmed them. To encounter dark matter is to encounter something that defines the word intangible in its most absolute sense. The philosopher George Berkeley argued that to exist is to be perceivaci est percipi. If no mind perceives a thing, if no sense registers its presence, can it be said to exist at all? Dark matter forces us to confront this question not as a thought experiment, but as an empirical reality. Here is matter that cannot be perceived, yet whose existence is undeniable. Here is substance that fails every test of tangibility while passing every test of gravitational presence. Our language struggles with this paradox. We call it dark, but darkness is merely the absence of light, and dark matter is not an absence. It is a presence that happens to be electromagnetically neutral. We call it matter, yet it shares almost none of the properties we associate with materiality. It does not burn or freeze. It cannot be shaped or molded. It will not rust or decay. It exists in a category our everyday vocabulary was never designed to accommodate. Children learn about the world through interaction. They touch hot stoves and learn about heat. They drop toys and learn about gravity. They stack blocks and discover structural principles. Every lesson is grounded in direct experience, in the immediate feedback loop between action and consequence. But how does one learn about something that provides no feedback? How does the mind construct a model of an entity that never pushes back, never resists, never leaves a mark? Scientists have developed sophisticated techniques to infer dark matter's presence rotation curves, gravitational lensing, large-scale structure formation. Yet these remain indirect methods, observations of effects rather than the thing itself. We see galaxies rotating too quickly and deduce the presence of additional mass. We notice light bending around galaxy clusters and calculate the distribution of invisible matter. We are forever reading shadows on the wall of Plato's cave, inferring the shapes of objects we cannot turn around to see. This mode of understanding is not unfamiliar to science. Much of modern physics operates through inference. We do not see atoms directly, but we observe their effects in cloud chambers and crystalline structures. We do not perceive magnetic fields with our senses, but we map them with iron filings and compass needles. The history of science is largely a history of developing instruments and methods to extend perception beyond its biological limits. Dark matter pushes this approach to an extreme. It asks us to accept the existence of something that may never be directly detectable. Its properties might remain forever beyond the reach of laboratory experiment. We must build our understanding entirely on gravitational effects, on the way it shapes the visible universe while remaining separate from it. The psychological weight of this realization is considerable. We are forced to acknowledge that the majority of the matter in the universe occupies a realm fundamentally inaccessible to human experience. We cannot touch it. We cannot see it. We cannot even, in principle, build a container to hold it, because it would pass through any material wall as if the wall were not there. This is not a temporary gap in our knowledge, waiting to be filled by better instruments or more sensitive detectors. This is a permanent feature of reality's architecture. The universe has constructed itself in such a way that most of its matter will never interact with the electromagnetic force, and therefore will never be perceivable to any organism or instrument that relies on light, heat, or any other electromagnetic phenomenon. The challenge this presents is not merely technical, but conceptual. We are being asked to fundamentally reimagine what it means for something to exist. In everyday life, existence and interaction are synonymous. A chair exists because you can sit on it. A wall exists because you cannot walk through it. A flame exists because it warms your hands and illuminates the darkness. The entire edifice of common-sense reality rests on the principle that things make their presence known through their effects on other things. Dark matter obeys this principle only in the narrowest sense. It has gravitational effects, yes, but gravity is so weak at human scales that we live our entire lives barely noticing it, except as the constant downward pull we call weight. The gravitational influence of dark matter particles passing through your body at this moment is utterly negligible, unmeasurable by any conceivable instrument, lost in the noise of Earth's own gravitational field. So, in what sense does dark matter exist for us as experiencing beings? It does not exist in our perceptual world. It does not exist in our tactile world. It exists only in our mathematical world, in the equations that describe cosmic motion, in the models that explain galactic structure. It is real in the same way that the number pi is real not as an object you can hold, but as a necessity that makes the universe intelligible. This realization carries a strange kind of vertigo. We stand on a planet composed of ordinary matter surrounded by air we can breathe and light we can see, and yet we are simultaneously immersed in a vast ocean of dark matter, whose density we can calculate but whose presence we cannot feel. The Earth plows through this ocean as it orbits the Sun, and the dark matter particles flow through our world like ghosts through walls, indifferent to the complex chemistry and electromagnetic processes that constitute our lives. The metaphor of ghosts is tempting but imperfect. Ghosts, in folklore, are the remnants of interaction they are said to haunt because they once lived, because they retain some connection to the tangible world. Dark matter has never had such a connection. It has never emitted light, never participated in chemistry, never assembled into structures we would recognize as objects. It is not a ghost of something that once interacted. It is a fundamental category of existence that never interacted and never will. Our brains, confronted with this reality, seek familiar anchors. We imagine dark matter as a kind of fog or cloud, because those are our models for things that are present but diffuse. We picture it as particles, because we are accustomed to thinking of matter as particulate. These visualizations are useful for calculation, but misleading for intuition. Dark matter is not dim lighting or thin mist. It is not a reduced version of normal matter. It is categorically different, playing by rules that exclude most of the phenomena we associate with physical substance. Some physicists have proposed that dark matter might interact with itself through forces we do not yet understand it. Dark force analogous to electromagnetism but confined to the dark sector. If true, there might be dark atoms or dark molecules, complex structures formed from dark matter particles bound together by dark photons. There could be an entire dark chemistry playing out in parallel to our own, forever separated by the absence of shared interaction. This possibility is both fascinating and deeply alienating. It suggests that we might live in a universe that contains rich complexity and structure we can never access civilizations of dark matter. Such a thing were possible that could occupy the same space we do without ever knowing we exist or we knowing of them. Two realities, interpenetrating, but forever isolated, like two radio stations broadcasting on frequencies too far apart to interfere. Whether such complexity exists in the dark sector remains unknown. The evidence so far suggests dark matter is simpler than ordinary matter, lacking the rich tapestry of forces and particles that allow chemistry and biology. But the point stands. We cannot rule out the existence of structures and processes in the dark sector that are simply invisible to us, not just in practice, but in principle. This brings us to a deeper question about the nature of knowledge itself. Science has always been the practice of extending perception through instrumentation and inference. The telescope let us see distant stars. The microscope revealed cells and bacteria. The particle accelerator made quarks and bosons accessible to study. Each advance pushed back the frontier of the observable. But what do we do when we encounter something that cannot be observed, even in principle, through any electromagnetic means? We are forced to rely entirely on gravitational inference, measuring how dark matter affects the motion of things we can see. We become archaeologists of gravity, piecing together the shape of the invisible from the distortions it creates in the visible. This is not a comfortable position for creatures who evolved to trust their senses. We want to see things, to touch them, to confirm their reality through multiple channels of perception. Dark matter offers none of these confirmations. It asks us to believe in its existence based on logic, and mathematics alone, based on the fact that without it, the universe does not make sense. And yet we do believe, not through faith, but through the accumulation of evidence so consistent and so robust that denial becomes untenable. Every galaxy surveyed, every cluster analyzed, every computer simulation run all point to the same conclusion. The dark matter is there. It has always been there. It shapes the cosmos at every scale. Our inability to perceive it directly is not its problem. It is ours. This realization marks a maturation in our understanding of existence. We are learning to accept that the universe is under no obligation to make itself fully perceptible to us. Reality is not constrained by the limitations of human neurology. The fact that our eyes register only a narrow band of the electromagnetic spectrum does not mean that other wavelengths are less real. The fact that our sense of touch detects only certain scales of pressure does not mean that neutrinos and dark matter particles, passing through us by the trillion, are somehow less substantial. We are guests in a universe that was not designed for our comprehension. Our senses give us a local, limited view sufficient for survival, insufficient for complete understanding. The cosmos operates on principles that span scales from the Planck length to the size of the observable universe, across timescales from fractions of a nanosecond to billions of years. We occupy one tiny bandwidth of this vast spectrum, and our intuitions are calibrated accordingly. Dark matter exists outside that bandwidth. It is operating in the same space at the same time, but on channels we cannot tune our instruments to receive. We know it is there because we can see its effects, the way a sailor knows the wind is blowing by watching the sails fill, even though air itself is invisible. The cognitive horizon we face is not merely about dark matter. 'Tis about accepting that much of reality might always remain beyond direct experience. The universe contains scales too small for us to visualize, durations too long for us to comprehend, and now entire categories of matter too non-interactive for us to perceive. Our minds, shaped by natural selection for survival in one particular environment, must stretch to accommodate a reality that includes much more than that environment ever hinted at. This is not a limitation to be overcome. It is a condition to be acknowledged. We are finite beings attempting to comprehend an infinite universe. We are electromagnetic creatures trying to understand a cosmos where most of the matter is electromagnetically inert. The gap between our sensory apparatus and the full complexity of existence is not a temporary inconvenience, but a permanent feature of our situation. And so we learn to navigate by inference, by calculation, by the slow accumulation of indirect evidence. We build mathematical models that predict the behavior of things we cannot see. We trust in the consistency of natural law, in the reliability of gravity, in the correspondence between theory and observation. We become comfortable with the idea that understanding does not require touching, that knowledge does not demand visibility. The dark matter is there, surrounding us, supporting the architecture of galaxies, shaping the destiny of the cosmos. It has been there since the beginning, and it will remain long after the last star burns out. It does not need our perception to validate its existence. It simply is, indifferent to our cognitive limitations, playing its silent role in the machinery of the universe. We can deduce it, we can map it, we can model it, but we cannot know it the way we know the warmth of sunlight or the solidity of stone. And perhaps that is the lesson that knowing comes in many forms. And the most important truths are often the ones that lie just beyond the reach of our senses, accessible only to the disciplined patience of scientific reasoning. Gravity is the universe's most honest accountant. Unlike light, which can be absorbed, scattered, or hidden behind clouds of dust, gravity cannot lie. Every particle of mass, regardless of its nature, contributes to the gravitational field. A photon-emitting star and a completely dark object of equal mass pull on their surroundings with identical strength. Gravity does not distinguish between the luminous and the invisible. It does not favor the bright over the dim. It simply responds to the presence of mass, indifferent to whether that mass announces itself through any other means. This impartiality makes gravity our most reliable witness to the contents of the universe. Newton was the first to formalize this relationship, to recognize that the same force pulling an apple toward the ground also holds the moon in orbit around the Earth, and the planets in their paths around the sun. His law of universal gravitation was elegant in its simplicity. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. The farther apart two objects are, the weaker their gravitational pull on each other. The more massive they are, the stronger the attraction. This inverse square law had immediate, testable consequences. It predicted the elliptical orbits of planets, the trajectories of comets, the timing of eclipses. It unified celestial and terrestrial mechanics under a single principle. For more than 2 centuries, Newton's gravity reigned as one of the most successful theories in the history of science. But Newton's framework, for all its precision, was incomplete. It described how gravity behaved, but not what gravity was. It treated gravitational attraction as a force transmitted instantaneously across empty space, with no mechanism for how one mass could know about the presence of another. The theory worked beautifully for calculation, but offered no deeper insight into the nature of the phenomenon it described. Einstein provided that insight. In his general theory of relativity, Einstein reconceived gravity not as a force at all, but as a consequence of geometry. Mass does not pull on other mass across empty space. Instead, mass curves the fabric of space-time itself, and objects moving through that curved space-time follow paths that appear, from our perspective, to be shaped by a gravitational force. A planet orbiting a star is not being pulled by an invisible tether, but is traveling along the straightest possible path through a region of spacetime that the star's mass has warped into a valley. This was not merely a philosophical reframing. Einstein's equations made predictions that differed from Newton's in subtle but measurable ways. The orbit of Mercury, which had troubled astronomers with its slow precession that Newton's equations could not fully explain, was accounted for precisely by general relativity. Light from distant stars passing near the Sun during a solar eclipse was observed to bend by exactly the amount Einstein predicted a deflection caused by the Sun's gravitational warping of spacetime. General relativity revealed gravity to be a property of the universe's structure, a distortion in the very stage on which all events unfold. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. This reciprocal relationship, this feedback loop between mass and geometry, is what we experience as gravitation. For the purposes of detecting dark matter, both frameworks, Newton's and Einstein's, provide essential tools. At the scale of galaxies and galaxy clusters, where velocities are relatively modest and gravitational fields, though vast in extent, are not extreme, Newton's simpler equations are often sufficient. They allow us to calculate the mass required to produce observed motions with straightforward arithmetic. When precision demands it, or when dealing with particularly strong gravitational effects like those near black holes or in the cores of massive clusters, Einstein's more complete description becomes necessary. What both frameworks share is their democratic nature. They respond to all mass equally. A kilogram of dark matter curves spacetime just as much as a kilogram of ordinary matter. From gravity's perspective, there is no difference. This equality is what allows us to detect dark matter at all. Though it emits no light and interacts with ordinary matter only through the weakest of forces, dark matter participates fully in the gravitational field. It contributes to the curvature of spacetime. It influences the motion of everything around it. Galaxies became the proving ground for this gravitational forensics. In the 1970s, astronomer Vera Rubin and her colleagues undertook careful studies of spiral galaxies, measuring the rotational velocities of stars and gas clouds at various distances from the galactic center. The technique was straightforward. By analyzing the Doppler shift of light emitted by these objects, how much the wavelength was stretched or compressed by their motion, they could determine how fast each region of the galaxy was moving. The expectation, based on the distribution of visible matter, was clear. Most of the luminous mass in a spiral galaxy is concentrated in the central bulge and the bright disk. As you move outward, toward the sparse outer regions, the amount of visible matter drops off sharply. According to Newton's laws, the orbital velocity of stars in these outer regions should decrease correspondingly. Just as the outer planets in our solar system move more slowly than the inner ones, stars at the edge of a galaxy should orbit more leisurely than those near the dense core. The rotation curve graph plotting orbital velocity against distance from the galactic center should rise to a peak in the dense inner regions and then decline steadily as you move outward. This is what the visible mass distribution predicted. This is what every reasonable model suggested. But the observations told a different story. The rotation curves did rise in the inner regions, as expected. But then, instead of declining, they remained flat. While stars at the outer edges of galaxies were moving just as fast as those closer in, sometimes even faster. This was not a subtle discrepancy or a borderline anomaly. The difference between prediction and observation was dramatic and consistent across every spiral galaxy surveyed. Something was holding those outer stars in their swift orbits. Something was providing additional gravitational pull, keeping the rotation curve flat far beyond where the visible matter tailed off. If you calculated the mass required to produce these velocities, it vastly exceeded the mass of all the stars, gas, and dust you could see. The numbers were unambiguous. The visible matter in a typical spiral galaxy might account for 10 or 15% of the total gravitating mass. The rest, the vast majority, was invisible. This was not a matter of missing a few dim stars or underestimating the amount of interstellar gas. The deficit was far too large. You would need to add 5 or 6 times as much ordinary matter as was visible to explain the rotation curves. And there was simply no plausible way that much normal matter could be hiding. Stars, even faint ones, emit light. Gas clouds glow when heated or block light when cold. Dust absorbs and re-radiates in the infrared. Every survey across every wavelength confirmed that the visible matter inventory was relatively complete. Yet the rotation curves remained flat, testifying to the presence of mass that made no electromagnetic appearance whatsoever. The pattern held across galaxies of different sizes, different morphologies, different distances. Large spirals and small irregulars, galaxies rich in gas and those nearly depleted dull, showed the same signature. The visible matter traced out spiral arms and central bulges, while something else, something dark, formed enormous halos extending far beyond the visible disk. These dark halos were not optional embellishments. They were structural necessities. Without them, the galaxies would tear themselves apart. The stars at the outer edges, moving at their observed velocities, would escape into intergalactic space within a few rotations. The spiral arms would unwind. The entire structure would dissolve. The gravitational evidence painted a specific picture of how dark matter must be distributed. It could not be concentrated at the galactic center because that would not produce the observed flat rotation curves. It had to be spread throughout the galaxy and beyond, forming a roughly spherical halo that extended 2 or 3 times farther than the visible disk. The density of this halo would be greatest near the center and would gradually decrease with distance, but never so steeply that the outer regions were left gravitationally bereft. Computer models confirmed this architecture. When astrophysicists simulated galaxies with dark matter halos of the appropriate shape and mass, the resulting rotation curves matched observations beautifully. The flat profile emerged naturally from the combination of visible matter concentrated in the disk and dark matter distributed in the halo. Remove the dark matter from the simulation and the galaxies became unstable, their stars scattering or collapsing depending on the details of the initial conditions. The dark matter halo was not a minor correction to galactic structure. It was the dominant component. The luminous matter, the stars and nebulae we photograph in exquisite detail occupied only the inner region of a much larger dark edifice. The galaxy we see is nested within a galaxy we cannot see, like a bright nucleus surrounded by a vast, invisible shell. This realization extended to galaxy clusters as well. When astronomers measured the velocities of individual galaxies within large clusters, they found speeds that implied total cluster masses far exceeding the sum of all visible galaxies. The galaxies themselves were moving too fast to be held together by their own combined gravity alone. There had to be additional mass distributed throughout the cluster and in the space between galaxies, providing the gravitational glue that kept the structure bound. Gravitational lensing provided independent confirmation. Einstein's general relativity predicts that massive objects bend the paths of light rays passing nearby. When light from a distant galaxy travels through or near a massive galaxy cluster, the cluster's gravity deflects the light, distorting the image of the background galaxy into arcs or multiple images. By analyzing these distortions, astronomers can map the distribution of mass in the cluster, all the mass, not just the luminous portion. These lensing studies revealed that the majority of a cluster S mass does not coincide with the positions of visible galaxies. Instead, it forms a smooth distribution throughout the cluster volume, with concentrations where galaxies are densest but extending far into the apparently empty space between them. The dark matter is there, interspersed with the galaxies, dominating the gravitational landscape. Some of the most striking evidence came from collisions between galaxy clusters. When two massive clusters merge, the galaxies themselves, separated by vast distances, pass through each other largely unscathed. They are too far apart to collide directly. The hot gas that fills the space between galaxies, however, does interact. As the two gas clouds meet, they collide and slow down, creating friction and generating X-ray emission that reveals their location. The dark matter, being non-interacting except through gravity, behaves like the galaxies themselves. It passes through the collision without slowing. Gravitational lensing maps of these merging clusters show that the majority of the mass, the dark matter, has continued moving past the point of collision, while the visible gas has been left behind, glowing in X-rays at the collision site. The dark matter and the ordinary matter have been spatially separated, a smoking gun demonstrating that the dark component is indeed distinct from the gas and stars. The bullet cluster, observed in detail in the early 2000s, provided perhaps the clearest example of this phenomenon. Two galaxy clusters had collided at tremendous speeds, and the aftermath was frozen in the sky for astronomers to analyze. The hot gas, visible in X-ray images, marked the collision point. The galaxies had passed through relatively undisturbed, and the gravitational lensing signal showing where the mass actually was peaked, not at the X-ray emission, but at the locations of the galaxy concentrations where the dark matter had traveled after passing through the collision. This observation was difficult to explain with alternative theories that attempted to avoid dark matter by modifying the laws of gravity. Modified gravity theories predicted that the gravitational field should be strongest where the ordinary matter was most concentrated, which would be at the X-ray emission peaks. But the lensing showed the opposite. The mass was where the dark matter should be, separated from the bulk of the ordinary matter. It was a direct, visual demonstration that something invisible and non-interacting was contributing the majority of the gravitational mass. Gravity, then, serves as our primary instrument for mapping the dark sector. We cannot see dark matter directly, but we can trace its outline by observing how it shapes the motion and distribution of things we can see. The rotation curves of spiral galaxies, the velocity dispersions of cluster members, the bending of light around massive structures, the separation of mass and light in colliding clusters. Each of these phenomena is a gravitational signature, a fingerprint left by dark matter in the patterns of motion and curvature throughout the universe. This forensic approach requires patience and precision. We must measure velocities to high accuracy, map the distribution of visible matter carefully, account for uncertainties and systematic errors. We must compare observations against theoretical predictions, testing whether the dark matter hypothesis consistently explains what we see. The process is iterative, cumulative, building confidence through the concordance of multiple independent lines of evidence. What emerges from this careful work is a coherent picture. Dark matter exists in quantities roughly 5 times greater than ordinary matter. It is distributed in halos around galaxies and throughout galaxy clusters. It does not clump as densely as ordinary matter because it lacks the ability to radiate energy and collapse into compact structures. It forms the gravitational scaffolding upon which all large-scale structure is built. The precision of this picture is remarkable, given that it is based entirely on gravitational inference. We have never captured a dark matter particle in a detector. We have never measured its temperature or density directly. We have never observed it emitting, absorbing, or scattering any form of radiation. And yet, we know how much of it there is, where it is located, and how it behaves, all because gravity cannot hide the presence of mass. This is the power of gravitational analysis. It transforms an invisible substance into a mappable, quantifiable component of cosmic structure. It allows us to weigh things we cannot see, to chart the distribution of matter that refuses to shine. Gravity becomes our telescope into the dark sector, our only reliable means of studying the majority of the universe's mass. The realization that gravity is both a force of nature and a diagnostic tool represents a conceptual shift in how we approach cosmology. We are no longer limited to studying only what emits light. We can investigate anything that has mass, anything that curves space-time, anything that influences the motion of other objects. The universe has become transparent to our gravitational probes in ways it never was to our optical telescopes. Dark matter, for all its invisibility, has been revealed by the very force it cannot escape. It bends space-time. It shapes orbits, holds galaxies together. And in doing so, it leaves traces subtle but undeniable in the motions of stars and the paths of light. These traces are sufficient. They tell us that we are not alone in the universe's accounting of mass. They tell us that the visible is the minority and that the majority operates in silence, revealed only through its gravitational presence. The rotation curves remain flat at the edges of spiral galaxies, testimony to halos we cannot photograph. The galaxies within clusters move too swiftly for their visible mass, testimony to dark matter filling the voids between them. Light bends around structures that do not glow, testimony to mass that warps space-time without radiating. Every observation is a thread in a tapestry that depicts a universe far richer and stranger than our eyes alone could ever reveal. Gravity has become our language for speaking with the darkness. It is a slow language, requiring careful observation and mathematical translation. But it is reliable. It is universal. And it is, for now, the only conversation we can have with the invisible architecture that holds the cosmos together. Through gravity, the dark matter speaks not in words or images, but in the precise mathematics of motion, in the curvature of space-time, in the silent testimony of galaxies that refuse to fly apart despite every visible reason they should. Light travels in straight lines through empty space. This principle, simple and seemingly inviolable, forms the foundation of how we interpret the cosmos. When we look at a distant star, we assume the photons reaching our eyes have traveled an undeviating path across the void. When we photograph a galaxy, we trust that its image represents its true position on the sky. Geometry and optics, combined, allow us to map the universe with confidence. But space is not empty, and it is not flat. Einstein showed us that mass warps the geometry of space-time itself. A massive object creates a depression in the fabric of reality, like a bowling ball placed on a stretched rubber sheet. Light, traveling through this warped region, follows the curves of space-time. From our perspective, the light's path bends. What appears to be a straight line through space is actually a curved trajectory through geometry that has been distorted by the presence of mass. For most purposes, this bending is negligible. The gravitational field of Earth, or even the Sun, produces deflections far too small to notice in everyday observation. But when light passes near extremely massive objects, galaxy clusters containing the gravitating mass of hundreds or thousands of galaxies, the deflection becomes significant. The light's path curves noticeably. Images distort. The universe becomes a hall of mirrors. This phenomenon, predicted by general relativity and confirmed during the solar eclipse of 1919, is called gravitational lensing. The massive object acts as a lens, not through any optical property, but through its gravitational warping of space-time. Light from sources behind the lens is bent as it passes through the distorted region, and the resulting image, as seen by a distant observer, is altered in predictable ways. The effects depend on the geometry of the alignment. If the massive lens and the background source are perfectly aligned with the observer, the image of the background source can be stretched into a complete Ring-an-Einstein ring, named after the man who first described this possibility. More commonly, the alignment is imperfect, and the image is distorted into arcs or multiple separate images scattered around the lens. For decades, gravitational lensing was a curiosity, a relativistic effect observed only in special cases where chance alignments and exceptionally massive lenses created dramatic distortions. But as telescopes improved and surveys went deeper, astronomers began to realize that lensing was not rare. It was ubiquitous. Nearly every massive galaxy cluster was lensing background galaxies to some degree. The universe was filled with gravitational optics, warping and redirecting light across billions of light-years. This revelation transformed lensing from an interesting effect into a powerful tool. If you could measure the distortions precisely how much a background galaxy's image had been stretched or bent, you could calculate the mass of the lens responsible for the distortion. And because gravitational lensing responds to all mass, not just luminous mass, it provided a direct way to map the total matter distribution, including dark matter. The technique is elegant in its directness. You do not need to know what kind of matter is doing the lensing. You do not need to understand its composition or temperature or any other property. You simply measure the distortion of light and use Einstein's equations to work backward from effect to cause, from bent image to mass distribution. Gravitational lensing is, in essence, a cosmic weighing scale that measures everything, visible or invisible. The first step is identifying which galaxies in an image are background sources and which are part of the foreground cluster. Distance is determined through redshift, the stretching of light's wavelength caused by the expansion of the universe. Galaxies that are farther away have higher redshifts. Their light shifted more dramatically toward the red end of the spectrum. By measuring redshifts, astronomers can establish a three-dimensional picture of which objects are in front and which are behind. The background galaxies, those with higher redshifts, provide the light that will be lensed by the foreground cluster. In the absence of lensing, these galaxies would appear as small, faint, undistorted shapes. But when their light passes through the gravitational field of a massive cluster, their images are transformed. They stretch into arcs. They multiply into multiple images. They brighten as their light is focused toward the observer, phenomenon called gravitational magnification. The degree of distortion depends on the mass of the cluster and the geometry of the alignment. A cluster with more mass creates stronger deflections. Background galaxies that pass closer to the cluster center are distorted more severely than those whose light skirts the edges. By measuring many background galaxies at different positions around the cluster, astronomers can map how the lensing strength varies across the field. This map of lensing strength translates directly into a map of mass. Strong lensing in a particular region indicates high mass concentration. Weak or absent lensing indicates lower mass. The technique is sensitive enough to reveal not just the total mass of the cluster, but its distribution. Where the mass is concentrated, where it is diffuse, how it extends into the spaces between galaxies. What these maps reveal is striking. The mass distribution does not match the light distribution. Visible galaxies mark the locations of some mass concentrations, but the total mass extends far beyond the positions of galaxies. The gravitational field is smoothly distributed throughout the cluster, with the dark matter filling the voids, creating a continuous medium in which the galaxies are embedded like fruits in gelatin. In some cases, the separation is even more dramatic. The bullet cluster, observed in exquisite detail, shows the hot gas glowing in X-rays and representing the majority of the ordinary matter concentrated at one location, while the gravitational lensing signal peaks elsewhere, offset from the gas. The dark matter, unimpeded by the collision that slowed the gas, has continued forward. The lensing map reveals its position unambiguously. The majority of the mass is where no ordinary matter glows. This spatial separation is something optical astronomy alone could never have discovered. Photographs show galaxies and, with X-ray telescopes, hot gas. But without gravitational lensing, the dark matter would remain invisible and unmappable. Lensing provides a way to see the gravitational field directly, to visualize the curvature of spacetime as a tangible, measurable quantity. The process of creating these mass maps involves sophisticated analysis. Each background galaxy must be carefully measured. Its shape in the absence of lensing must be estimated, a challenging task, since galaxies have intrinsic shapes that are not circular. Statistical methods are employed, averaging over hundreds or thousands of background galaxies to separate the systematic distortion caused by lensing from the random variations in galaxy shapes. The result is a convergence map, a representation of how much mass lies along each line of sight through the cluster. High convergence means high projected mass. Low convergence indicates less mass. These maps are often rendered in false color, with bright regions representing dense concentrations of matter and dark regions showing where mass is sparse. When these lensing-derived mass maps are compared to images of the cluster's visible light, the discrepancy is obvious. The light comes from discrete galaxies scattered across the field. The mass is distributed more broadly, smoothly, filling the entire volume of the cluster. The galaxies sit within a vast halo of dark matter that has no optical counterpart. The technique of gravitational lensing extends beyond massive galaxy clusters. Weak lensing, a more subtle form of the phenomenon, can detect dark matter even in regions where the distortions are too slight to create dramatic arcs. Individual galaxies, far less massive than galaxy clusters, still warp spacetime enough to produce measurable effects on background sources. The distortions are small often, just a few % change in a galaxy's apparent shape with large enough samples. The signal emerges from the noise. Weak lensing surveys map the large-scale distribution of matter across vast swaths of sky. They reveal the cosmic web, the network of filaments and voids that characterizes the universe's structure at the largest scales. Dark matter, traced by weak lensing, forms the backbone of this web. The filaments are highways of dark matter connecting massive nodes where galaxy clusters reside. The voids are regions of low density where little matter of any kind exists. These maps show a universe that is far more structured than the smooth distribution of galaxies alone would suggest. The dark matter web emerged early in cosmic history, its structure seeded by tiny fluctuations in the density of the primordial universe. Gravity amplified these fluctuations over billions of years, pulling matter together along preferential axes, creating the filamentary network we observe today. Ordinary matter, responding to the gravitational potential wells created by dark matter, flowed along these same filaments, accumulating in the densest regions and forming galaxies. The cosmic microwave background, the ancient light from the early universe, carries additional lensing information. As this light travels toward us from the moment of recombination roughly 380,000 years after the Big Bang, it passes through all the intervening structure that is formed since the mass along this incredibly long line of sight deflects the light, distorting the pattern of hot and cold spots in the microwave background. By comparing the observed pattern of the microwave background to models of what it should look like without lensing, cosmologists can extract the lensing signal and use it to map the distribution of matter throughout cosmic history. This is deep field archaeology, using the most ancient light available to probe the dark matter that has shaped the universe's evolution. The consistency across all these different lensing methods is reassuring. Strong lensing in galaxy clusters, weak lensing in large-scale structure surveys, and cosmic microwave background lensing all point to the same conclusion. Dark matter exists in the amounts and distributions predicted by models of structure formation. The universe's matter content is dominated by something invisible, something that makes itself known only through gravity. What gravitational lensing provides is a form of direct observation that circumvents the limitations of electromagnetic astronomy. We are not inferring dark matter's presence from the motion of stars or the dynamics of galaxies, though those remain important lines of evidence. We are seeing the curvature of space-time itself, measuring the geometry of the gravitational field in 3 dimensions. The bent arcs of lensed galaxies are photographs of warped space, visual representations of Einstein's equations made manifest. This is as close as we can come to imaging dark matter. We cannot photograph the particles themselves, they emit no light. We cannot capture their silhouettes, they do not block light. But we can photograph the distortions they create, the fingerprints they leave in the geometry of space. Each elongated arc, each Einstein ring, each subtle statistical distortion in the shapes of background galaxies is a signature of dark matter's gravitational presence. The precision of these measurements continues to improve. Modern telescopes equipped with sensitive cameras and sophisticated optics can detect lensing distortions with remarkable accuracy. Surveys covering large fractions of the sky compile millions of galaxy images, building statistical power that allows even weak signals to be extracted reliably. Machine learning algorithms assist in classifying galaxies, measuring shapes, and identifying lensing features with speed and consistency that human analysis could never achieve. The Hubble Space Telescope has provided some of the most stunning images of strong gravitational lensing, capturing Einstein rings and multiple image systems with clarity impossible from ground-based observatories. The James Webb Space Telescope, with its infrared sensitivity and high angular resolution, extends this capability to even more distant sources, probing the universe when it was younger and the cosmic web was still forming. These observations are not merely aesthetic achievements. Each image contains quantitative information about mass distribution, about the relationship between dark and luminous matter, about the growth of structure over cosmic time. The beauty of an Einstein ring is matched by its scientific utility, perfect fusion of the universe's elegance and its investigability. What emerges from decades of lensing studies is a detailed portrait of dark matter's role in cosmic architecture. It forms halos around every galaxy, with density profiles that can be measured and compared across different galaxy types. It fills the space between galaxies in clusters, contributing 5 to 10 times more mass than all the visible galaxies combined. It defines the large-scale structure of the universe, creating the gravitational framework within which galaxies and stars and planets can form. This dark framework is not static. It evolves as the universe expands and ages. The cosmic web grows more pronounced as gravity continues to pull matter into filaments and nodes. Galaxy clusters grow more massive as smaller structures merge into them. Dark matter halos accrete more mass from their surroundings, though at a slowing rate as the universe's expansion accelerates and structure growth is suppressed at the largest scales. Gravitational lensing allows us to track this evolution. By observing clusters at different redshifts, different distances, and therefore different epochs in cosmic history, astronomers can measure how the dark matter distribution has changed over time. Early clusters were less massive, their dark matter halos still growing rapidly. Recent clusters are more mature, their growth having slowed as the universe's expansion counteracts the inward pull of gravity. The technique has also revealed surprises. Some galaxy clusters show asymmetric mass distributions, evidence of recent mergers or ongoing accretion. Others display unexpected substructures within their dark matter halos, clumps and filaments that hint at the complex history of how the cluster assembled. Occasionally, lensing reveals massive concentrations of dark matter in regions where few visible galaxies exist, dark nodes in the cosmic web that have yet to accumulate significant amounts of star-forming matter. Each discovery refines our understanding of how dark matter behaves, how it clumps and flows, how it interacts with itself gravitationally while remaining aloof from the electromagnetic drama of ordinary matter. The lensing observations constrain theoretical models, ruling out some possibilities and supporting others. They test whether dark matter is truly collisionless or whether it might have subtle self-interactions that affect its distribution on small scales. The power of gravitational lensing lies in its model independence. Unlike dynamical studies that require assumptions about equilibrium or orbital stability, lensing measures mass directly from geometry. Einstein's equations connect space-time curvature to mass density without requiring intermediate steps or additional assumptions about the nature of the matter. The light bends. The equations predict how much mass is required to produce that bending. The conclusion follows inevitably. This directness makes lensing the gold standard for measuring dark matter. It is the technique that convinced many skeptics, the observation that could not be easily explained away by alternative theories. When the bullet clusters showed the mass and light separated in space, when lensing maps revealed dark matter concentrations where nothing glowed, the case for dark matter's existence became overwhelming. The universe, it turns out, is constantly distorting its own image. Every massive structure along our line of sight to distant galaxies acts as a lens, bending light and modifying what we see. The deep images we take of the cosmos are not direct views, but composites of countless lensing events, each one adding subtle distortions, each one carrying information about the distribution of mass. We have learned to read these distortions, to decode the language of warped space. We have built algorithms and models that translate bent arcs into mass maps, that convert statistical shear patterns into measurements of dark matter density. We have turned the universe's gravitational complexity from an obstacle into an asset, using the very thing that distorts our view to reveal what cannot otherwise be seen. The lens of gravity, once understood, becomes transparent. We see through the distortions to the mass that causes them. We map the invisible by tracing its influence on the visible. And in doing so, we render the dark matter for all its refusal to emit, absorb, or scatter light visible after all. Not as an object, but as a shape, a distribution, a presence sculpted in the geometry of space-time itself. Fritz Zwicky was not known for his tact. The Swiss-American astrophysicist, working at the California Institute of Technology in the 1930s, possessed a mind that moved faster than diplomacy allowed. He coined terms that would endure in physics supernova, neutron stars, and he pursued ideas with an intensity that often alienated his colleagues. But Zwicky's abrasiveness concealed, or perhaps accompanied, an uncommon willingness to follow data wherever it led, regardless of how strange the destination. In 1933, Zwicky turned his attention to the Coma Cluster, a rich congregation of galaxies located roughly 300 million light-years from Earth. Using the newly available spectroscopic techniques, he measured the velocities of individual galaxies within the cluster, tracking how fast they moved relative to the cluster's center of mass. The measurements were challenging, requiring long exposures and careful analysis, but the results were clear. The galaxies were moving far too quickly. Zwicky applied the virial theorem, a relationship from classical mechanics that connects the kinetic energy of a system to its gravitational potential energy. For a stable bound system like a galaxy cluster, the theorem provides a way to estimate the total mass based on observed velocities. The faster the galaxies move, the more mass is required to keep them gravitationally bound and prevent the cluster from flying apart. When Zwicky performed the calculation for the Coma Cluster, the result was shocking. The total mass required to explain the observed velocities was roughly 400 times greater than the mass of all the visible galaxies combined. Even accounting for uncertainties in the measurements and the assumptions underlying the virial theorem, the discrepancy was enormous. Zwicky did not hesitate to draw the radical conclusion. There must be matter in the cluster that was not visible dark matter, he called it. Dunkelmaterie in his native German. This unseen mass dominated the cluster's gravitational budget, providing the binding force necessary to hold the high-velocity galaxies together. The reaction from the astronomical community was muted at best. Zwicky's reputation for eccentricity made it easy to dismiss his findings as another of his provocations. The measurements themselves were at the edge of what was possible with 1930s technology, leaving room for doubt. Perhaps the velocities were wrong. Perhaps the virial theorem did not apply in this case. Perhaps there was ordinary matter present, dim stars, gas, dust that had simply been overlooked. More fundamentally, the idea of invisible matter felt like a defeat, an admission that the universe was not yielding its secrets to observation. Astronomy had always been about seeing farther, more clearly, cataloging the visible contents of the cosmos. The suggestion that most of the universe's mass might be permanently hidden felt less like a discovery and more like a failure of technique. Zwicky's paper was published, noted, and largely set aside. The dark matter problem, as he had framed it, languished for decades. It was an anomaly, certainly, but one that could be deferred, left for future instruments or future theories to resolve. The universe was large and complex. Not every puzzle needed immediate solution. The issue resurfaced, quietly at first, in studies of individual galaxies. In the 1960s and 1970s, improvements in spectroscopy and radioastronomy made it possible to measure the rotation of galaxies with unprecedented precision. Astronomers could track not just the motion of stars in the bright galactic cores, but also the velocities of gas clouds in the faint outer regions where stars were sparse. The technique involved measuring the Doppler shift of emission lines, particularly the 21-centimeter line emitted by neutral hydrogen, and using these shifts to construct rotation curves showing orbital velocity as a function of distance from the galactic center. Vera Rubin, working at the Carnegie Institution of Washington, became one of the leading figures in this work. Trained as an astronomer at a time when women were often discouraged from pursuing science, Rubin had developed expertise in galaxy kinematics, the study of how galaxies rotate and how their constituent parts move. Her approach was methodical, painstaking, characterized by attention to detail and skepticism of premature conclusions. In collaboration with instrument builder Ken Ford, Rubin undertook a systematic study of spiral galaxies, beginning with Andromeda, the nearest large spiral to our own Milky Way. The goal was straightforward: measure the rotation curve as far out as observations would allow and compare the results to the predictions based on visible matter. The expectation, grounded in Newtonian mechanics and confirmed by the behavior of our solar system, was clear. The rotation speed should peak in the dense inner regions where most of the luminous mass was concentrated, then decline steadily in the outer regions as the gravitational influence of the central mass weakened with distance. This Keplerian decline, named after Johannes Kepler, laws of planetary motion, was the natural consequence of a mass distribution dominated by a central concentration. But Andromeda did not cooperate. The rotation curve rose in the inner regions as expected, but instead of falling off, it remained flat, extending far beyond the visible disk. Stars and gas clouds at the galaxy's edge were orbiting just as fast as those much closer to the center. The implication was unavoidable. There had to be additional mass distributed throughout and beyond the visible galaxy. Mass that did not shine, but whose gravitational influence kept the outer regions moving at high speeds. Rubin and Ford expanded their survey to other spirals. Galaxy after galaxy showed the same pattern: flat rotation curves extending well beyond the optical disk. The anomaly was not specific to Andromeda. It was universal. The measurements were meticulous, the uncertainties carefully quantified. There was no obvious error in the technique, no systematic bias that could explain away the results. The data simply insisted that galaxies contained far more mass than could be accounted for by their stars, gas, and dust. Still, acceptance came slowly. Some astronomers suggested that the rotation curve measurements might be flawed, that the Doppler shifts were being misinterpreted, or that the gas clouds being measured were not in stable orbits. Others proposed that there might be vast quantities of ordinary matter in forms difficult to detect, cold gas that did not emit strongly, or populations of faint stars too dim to contribute significantly to the galaxy's light but numerous enough to provide the needed mass. These alternatives were tested and found wanting. Surveys across different wavelengths confirmed that the visible matter inventory was relatively complete. Cold gas would block background light or absorb specific frequencies. Neither effect was observed in sufficient quantity. Faint stars would still emit some light and contribute to the total luminosity. The required numbers would make galaxies far brighter than observed. The dark matter explanation, once marginalized as Zwicky's eccentricity, became increasingly difficult to avoid. The rotation curves were telling a consistent story. Galaxies were embedded in massive halos of non-luminous matter, halos that extended far beyond the visible disk and dominated the total gravitating mass. Rubin herself was cautious in drawing conclusions, preferring to present the data and let others debate the interpretation. But as the evidence accumulated not just from her work but from independent studies by other research groups using different methods, the pattern became undeniable. The visible components of galaxies were not gravitationally self-sufficient. They required the presence of something else, something dark, to remain stable. The parallels to Zwicky's earlier work became apparent. He had found that galaxy clusters contained too little visible mass to explain their dynamics. Rubin and others were now finding the same deficit within individual galaxies. The dark matter problem was not confined to the largest structures. It permeated every scale where gravity could be measured precisely. The slow accumulation of evidence created a cultural shift within astronomy. The question was no longer whether dark matter existed, but what it was and how it was distributed. The conversation moved from skepticism to investigation, from resistance to exploration. Conferences began dedicating sessions to the dark matter problem. Theorists proposed candidates for what the dark matter particles might be. Observers refined their measurements, extending rotation curves to greater distances, surveying more galaxies, looking for patterns that might constrain the nature of the unseen mass. This shift represented more than a change in scientific consensus. It marked a fundamental reorientation in how humanity understood its place in the cosmos. For centuries, the visible universe had seemed comprehensible, its contents catalogable, its behavior predictable. Stars were made of known elements governed by understood physics. Galaxies were collections of stars, gas, and dust components that could be observed, measured, and modeled. The universe might be vast, but it was composed of familiar ingredients arranged in complex but ultimately knowable configurations. The acceptance of dark matter shattered this comfortable picture. The universe was not what it appeared to be. The matter we are made of, the atoms that constitute stars and planets and living things, represented only a small fraction of the total mass. The rest was something else entirely. Something that did not participate in the electromagnetic interactions that define our experience of materiality. This was not merely a quantitative adjustment, a revision of cosmic inventories. It was a qualitative transformation in our understanding of what the universe contains. We had discovered that reality includes entire categories of substance fundamentally different from anything in our direct experience. The atoms that compose our bodies, that form the rocks beneath our feet and the air we breathe, were revealed to be atypical, a minority constituent in a cosmos dominated by something alien. The implications extended beyond astrophysics. Philosophy, which had long grappled with questions of existence and perception, now had to contend with empirical evidence that most of the universe's substance was imperceptible in principle. The old debates about the relationship between appearance and reality took on new dimensions. Here was matter that had no appearance, that could never be perceived through any electromagnetic means, yet whose existence was more certain than many things we encounter daily. Zwicky had anticipated this transformation, though he had not lived to see it fully realized. His willingness to propose dark matter in the 1930s, when the idea seemed outlandish, demonstrated a commitment to following evidence over intuition. He had trusted the calculations more than the comfort of familiar categories. The universe was telling him, through the velocities of galaxies in the Coma Cluster, that something invisible and massive was present. He reported what the data said, regardless of how strange it sounded. Rubin's work in the 1970s carried a different weight. By then, the technological capabilities had advanced enough that the measurements could not be easily dismissed as marginal or uncertain. The rotation curves were solid, reproducible, independently confirmed. The flat profiles extending beyond the visible disk were not artifacts or errors. They were features of nature, patterns that demanded explanation. Rubin herself remained focused on the observations, on the discipline of careful measurement and rigorous analysis. She was not given to speculation about the nature of dark matter or grand pronouncements about cosmic significance. Her contribution was in establishing the phenomenon beyond doubt, in providing the observational foundation upon which others could build theoretical structures. The combination of Zwicky's early insight and Rubin's meticulous confirmation created a turning point. The dark matter hypothesis transitioned from a speculative idea on the margins of acceptability to a central component of cosmological models. By the 1980s, it was becoming difficult to construct theories of galaxy formation and large-scale structure without invoking dark matter. The simulations that modeled the growth of cosmic structure from small initial fluctuations failed to reproduce observations unless significant amounts of non-baryonic dark matter were included. This convergence of evidence from multiple independent sources, galaxy dynamics, cluster dynamics, gravitational lensing, and cosmological simulations, built a case that transcended any single line of reasoning. Each method had its own uncertainties and potential systematic errors, but the fact that they all pointed to the same conclusion gave the dark matter hypothesis a robustness that no alternative could match. The resistance that had initially greeted Zwicky's proposal gradually dissolved, not because scientists became less skeptical or more willing to accept exotic explanations, but because the evidence accumulated to the point where skepticism itself required more elaborate contortions than acceptance. It became easier to believe in dark matter than to explain away the vast body of observations that pointed to its existence. This process, the slow, reluctant shift from doubt to acceptance, reflected the scientific method at its best. Ideas are not adopted because they are elegant or comfortable, but because explain observations better than competing proposals. Dark matter was not welcomed enthusiastically. It was accepted grudgingly, only after every reasonable alternative had been tested and found inadequate. The human cost of this transformation should not be overlooked. Zwicky's work was largely ignored during his lifetime, his contributions acknowledged only posthumously as the astronomical community came to recognize the importance of the dark matter problem he had identified. Rubin faced barriers throughout her career, working in a field that was often unwelcoming to women, her achievements sometimes minimized or attributed to her collaborators. Yet both persisted, driven by curiosity and commitment to understanding how the universe actually operates, rather than how it might be convenient for it to operate. Their work exemplified the integrity that science demands: the willingness to report unexpected results, to challenge prevailing assumptions, to let data override theoretical preferences. The turning point they represented was not a single moment, but a gradual accumulation of understanding. Zwicky's observations in the 1930s planted a seed. Rubin's work in the 1970s nurtured it into undeniable growth. By the 1980s and 1990s, the dark matter paradigm had taken root throughout cosmology, shaping how astronomers thought about galaxy formation, structure, growth, and the overall composition of the universe. What emerged was a humbling picture. Humanity had spent millennia cataloging the stars, mapping the galaxies, tracing the large-scale structure of the cosmos, only to discover that all of this effort had captured merely the luminous surface of a much deeper reality. The universe we could see was the exception, not the rule. The normal matter, if such a term made sense anymore, was the dark matter, present in quantities 5 or 6 times greater than the atoms we are made of. We were not the standard composition of the cosmos. We were the trace constituent, the minor byproduct. The universe had constructed itself primarily from something else, something that did not shine and never would. Our existence, our perception, our entire biological heritage was built upon a foundation of electromagnetic interaction, photons and electrons, chemistry and light. But the universe's foundation was built on gravity alone, on the silent accumulation of dark mass into the scaffolding upon which our visible reality draped itself. This realization stripped away layers of anthropocentric assumption. We were not just displaced from the center of the solar system, as Copernicus had shown, or revealed to be one species among millions on a planet orbiting an ordinary star. As Darwin and later astronomers demonstrated, we were now understood to be composed of atypical matter, our very substance a minority report in the cosmic census. The Zwicky and Rubin turning point was not about the triumph of 2 individuals, though their contributions were essential. It was about a species learning to see past its own limitations, to accept that the universe contains more than our senses or intuitions. Suggested to follow evidence into uncomfortable territory and remain there until understanding caught up with observation. The data had spoken. The galaxies rotated too fast. The clusters moved too swiftly. The universe weighed more than it shone. And slowly, reluctantly, but ultimately, irreversibly, humanity adjusted its picture of reality to accommodate this strange, persistent truth. The dark matter was there. It had always been there. It simply had not been ready to see it. If you could strip away all the light from the universe, all the stars and galaxies, all the glowing gas and radiant dust, what would remain is not emptiness, but architecture. The dark matter, invisible to every telescope and immune to every electromagnetic probe, forms a structure of staggering scale and complexity. It is organized into a vast network of filaments and nodes, a cosmic web stretching across billions of light years, connecting the densest concentrations of matter in a pattern that resembles neural pathways or the intricate scaffolding of a three-dimensional lattice. This web is not a metaphor. It is a physical reality, mapped through gravitational effects and confirmed by the distribution of galaxies throughout space. The filaments are highways of dark matter, regions where the density is higher than the cosmic average, creating gravitational channels along which ordinary matter flows. The nodes are intersections where multiple filaments meet, forming the gravitational anchors where galaxy clusters reside. Between the filaments lie voids, vast regions of lower density where little matter of any kind exists. The visible universe, the galaxies we photograph, the stars we catalog, the nebulae we admire, traces this underlying structure. Galaxies are not randomly scattered through space. They congregate along the dark matter filaments, forming chains and walls that outline the web. The largest galaxy clusters sit at the nodes, marking the points of maximum gravitational potential. The cosmic voids remain largely empty, their low density offering insufficient gravitational pull to retain matter against the universe's expansion. This arrangement is not coincidental. It is the direct consequence of how dark matter behaves and how structure grows from initial conditions. In the earliest moments after the Big Bang, the universe was extraordinarily uniform. The distribution of matter and energy was smooth to within 1 part in 100,000. But perfect uniformity was never achieved. Quantum fluctuations in the inflationary epoch seeded tiny variations in density, regions slightly denser than average, and regions slightly less dense. These fluctuations were minuscule, but they were enough. As the universe expanded and cooled, gravity began amplifying these initial perturbations. Regions that were slightly denser than average had a bit more gravitational pull, attracting surrounding matter and becoming denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming more rarefied. The process was self-reinforcing. Overdense regions grew denser. Underdense regions grew emptier. Dark matter played the critical role in this gravitational amplification because it began clumping earlier than ordinary matter. In the first few 100,000 years after the Big Bang, ordinary matter existed as a hot, ionized plasma, tightly coupled to radiation through constant electromagnetic interactions. The pressure of this radiation prevented the ordinary matter from collapsing into gravitational wells. Every attempt to clump was resisted by the outward pressure of photons scattering off charged particles. Dark matter, immune to electromagnetic forces, faced no such resistance. It felt only gravity. It could begin collecting into denser concentrations immediately, responding to the slight variations in the primordial density field without interference from radiation pressure. While ordinary matter remained diffuse and coupled to photons, dark matter was already forming the first structures. These dark matter concentrations created gravitational potential wells, depressions in the fabric of space-time that grew deeper as more dark matter accumulated. They were invisible, undetectable by any means other than their gravitational influence. But they were preparing the stage for what would come next. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, an event called recombination. Occurring roughly 380,000 years after the Big Bang, the ordinary matter decoupled from radiation. freed from the pressure of photons, the hydrogen gas could finally respond to gravity. And gravity directed it into the potential wells that dark matter had already excavated. The ordinary matter flowed along the gravitational gradients, falling into the dark matter concentrations. Where dark matter had formed filaments, hydrogen streamed along the same paths. Where dark matter had created nodes, hydrogen accumulated in the deepest wells. The cosmic web that dark matter had been constructing invisibly now began to fill with ordinary matter, the raw material that would eventually ignite into stars. This process of structure formation is captured in cosmological simulations, computer models that track the evolution of both dark and ordinary matter from the early universe to the present day. These simulations begin with the initial density fluctuations inferred from observations of the cosmic microwave background. They apply the known laws of gravity and fluid dynamics, tracking billions of particles as they interact and evolve over cosmic time. The results are striking. Without dark matter in the simulations, structure formation proceeds to slowly, the ordinary matter alone, starting from the tiny initial fluctuations, cannot clump into galaxies and clusters within the available time. The gravitational pull is insufficient. The universe remains too smooth, too uniform, bearing no resemblance to the richly structured cosmos we observe. But when dark matter is included in the simulations, in the proportions suggested by observational evidence, the results match reality with remarkable fidelity. The cosmic web emerges naturally. Filaments form connecting massive nodes. Voids expand as matter drains into denser regions. Galaxies appear at the expected locations and in the expected numbers. The large-scale structure of the simulated universe looks like the large-scale structure of the real universe. This concordance is powerful evidence that the cosmological models have captured something essential about how the universe works. The dark matter hypothesis is not merely explaining individual anomalies, rotation curves, or cluster dynamics. It is explaining the entire architecture of the cosmos, from the smallest galaxies to the largest structures spanning hundreds of millions of light-years. The cosmic web revealed by these simulations and confirmed by galaxy surveys is ancient. Its basic structure was established early in cosmic history. Within the first billion years after the Big Bang, the filaments and nodes that exist today are descendants of the patterns seeded by quantum fluctuations in the inflationary epoch, grown and refined by billions of years of gravitational evolution. The galaxies we see are relative latecomers. The first stars did not ignite until the universe was several hundred million years old, when the first pockets of hydrogen gas became dense enough to collapse under their own gravity and initiate nuclear fusion. These first stars formed within the dark matter halos that had been growing since the recombination era, their birth locations predetermined by the distribution of invisible mass. As generations of stars lived and died, enriching the gas with heavier elements, the protogalaxies grew more complex. Dark matter halos merged, their collisions triggering bursts of star formation. Smaller halos were absorbed into larger ones, building the massive galaxies we see in the nearby universe. Throughout this process, the dark matter provided the gravitational framework, the skeleton upon which the luminous components assembled themselves. The relationship is hierarchical. The dark matter web defines where structure can form. The filaments channel ordinary matter toward the nodes. The nodes become the sites of galaxy cluster formation. Individual galaxies form within dark matter, halos scattered along the filaments and concentrated at the nodes. The stars and gas within each galaxy respond to the gravitational potential of their host dark matter halo, their distribution and dynamics shaped by the invisible mass that contains them. This hierarchical structure operates at every scale. A single galaxy sits within a dark matter halo extending far beyond its visible disk. That galaxy is part of a group or cluster, which occupies a larger dark matter halo binding dozens or hundreds of galaxies together. The cluster itself is embedded in a filament of the cosmic web. Connected to other clusters through dark matter highways, spanning tens or hundreds of millions of light-years. The voids between filaments are not completely empty, but their density is low enough that galaxies rarely form there. The few galaxies that do exist in voids tend to be small, dim, and isolated, lacking the rich environment of mergers and interactions that characterize galaxies in denser regions. They are cosmic hermits, occupying the quiet spaces between the web's active threads. The cosmic web is dynamic, not static. It continues to evolve as the universe ages, though the pace of evolution has slowed compared to earlier epochs. Galaxy clusters are still growing through mergers and accretion. Filaments are still channeling matter toward the densest regions. But the universe's accelerating expansion, driven by dark energy, works against further structure growth at the largest scales. The cosmic web we observe today represents a mature configuration, its broad outlines unlikely to change dramatically in the future. Mapping this web has required decades of observational effort. Large-scale galaxy surveys measure the positions and distances of millions of galaxies, building three-dimensional maps of how matter is distributed throughout the observable universe. Projects like the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recent efforts using advanced telescopes have charted the locations of galaxies across vast volumes of space. These surveys reveal the filamentary structure directly. When galaxy positions are plotted in 3 dimensions, the cosmic web appears as a natural consequence of the data. Galaxies form thin sheets and elongated filaments surrounding vast voids. The pattern is unmistakable and consistent across different regions of the universe and different cosmic epochs. Weak gravitational lensing surveys provide complementary information, mapping the dark matter distribution directly rather than inferring it from the positions of luminous galaxies. These surveys measure the subtle distortions in galaxy shapes caused by intervening mass, building maps of the dark matter web that can be compared to the distribution of visible galaxies. The correlation is strong. Where dark matter concentrates, galaxies congregate. The luminous universe traces the dark scaffolding with high fidelity. The cosmic microwave background carries information about the web's earliest stages. The tiny temperature fluctuations in this ancient light, emitted when the universe was 380,000 years old, represent the primordial density variations that seeded structure formation. The pattern of these fluctuations, characterized by their statistical properties across different angular scales, encodes information about the initial conditions from which the cosmic web grew. By comparing the observed pattern of microwave background fluctuations to predictions from cosmological models, scientists can constrain the parameters governing structure formation, including the total amount of dark matter, the strength of the initial fluctuations, and the expansion rate of the universe. The agreement between observations and predictions is excellent, confirming that our models of how structure grows from initial perturbations are fundamentally correct. This convergence of evidence from galaxy surveys, gravitational lensing, cosmic microwave background observations, and numerical simulations builds an extraordinarily robust picture. The cosmic web is real. It is dominated by dark matter. It formed through gravitational instability, amplifying quantum fluctuations from the inflationary epoch. It provides the framework within which all visible structure exists. Without dark matter, this architecture would not exist. The universe would have expanded too smoothly, too uniformly. The initial fluctuations in ordinary matter alone would have been insufficient to grow into galaxies and clusters within the available time. The radiation pressure in the early universe would have suppressed structure formation in ordinary matter until much later, delaying the appearance of the first stars and galaxies by billions of years. Even if structure had eventually formed without dark matter, it would look nothing like what we observe. The distribution of galaxies would be different. The cosmic web would be absent or weak, and the large-scale patterns we see in galaxy surveys would not exist. The universe would be a fundamentally different place. likely to diffuse and unstructured to allow for the complex chemistry and gravitational environments necessary for planet formation and the emergence of life. Dark matter's role as cosmic scaffolding is not incidental. It is essential. The universe's structure depends on it. The formation of galaxies depends on it. The environment in which stars form, planets coalesce, and life arises depends on it. We exist because dark matter created the gravitational potential wells that allowed ordinary matter to accumulate and organize itself into the intricate structures we see today. This dependence places dark matter at the foundation of cosmic history. It was the first component to begin clumping after the Big Bang. It provided the gravitational seeds for structure formation. It channeled ordinary matter into the configurations that became galaxies. It continues to shape the evolution of cosmic structure. Even as the universe's expansion accelerates and the growth of new structures slows, the visible universe, the stars, planets, nebulae, and galaxies we observe and celebrate as, in this sense, a secondary phenomenon. It is the outcome of processes initiated and guided by dark matter. The luminous components are passengers on a dark vehicle, their trajectories determined by invisible gravitational fields, their locations predetermined by the architecture of the cosmic web. This is a humbling realization, but also a clarifying one. The universe has structure because dark matter has structure. The cosmic web exists because dark matter formed it first, providing the template into which ordinary matter flowed. The galaxies shine because they are embedded in dark matter halos that gathered the gas from which stars could form. The metaphor of scaffolding is apt. Scaffolding supports construction, provides the framework within which a building takes shape, and is typically removed once the structure is complete. But the cosmic scaffolding is permanent. It cannot be removed. It remains integral to the structure it supports, holding galaxies in their orbits, binding clusters together, maintaining the integrity of the cosmic web against the relentless expansion of space. The light we see is the finishing detail, the visible surface of a much deeper architecture. It is foam clinging to a dark lattice, bright tracery highlighting the outline of something vast and invisible. The stars and galaxies are important. Certainly, they are the sites of complexity, chemistry, and possibly life. But they are not the primary story. They are the illuminated consequence of a darker narrative, the visible result of processes that played out in the shadows of the electromagnetic spectrum. We live in a universe where the visible is the exception. The dark matter web is the rule. It is the fundamental structure, the gravitational skeleton upon which everything else is hung. Our own galaxy, the Milky Way, orbits within a dark matter halo that extends perhaps 10 times farther than the visible disk. Our local group of galaxies is bound together by dark matter pervading the space between us and Andromeda. The Virgo supercluster, of which our local group is a peripheral member, is held together by dark matter distributed throughout its volume. At every level, the dark matter is there, unseen but indispensable, providing the gravitational cohesion that prevents structures from dissolving into the expanding void. It is the silent partner in every cosmic interaction, the invisible hand guiding the distribution of matter across billions of light-years. The cosmic web will endure long after the last stars burn out. Dark matter does not decay. It does not radiate energy. It will persist indefinitely, maintaining its structure even as the luminous universe fades. In the far future, when star formation has ceased and galaxies have exhausted their fuel, the dark matter web will remain, an invisible monument to the universe's structural history, a ghost network outlining where light once traced patterns in the darkness. For now, we are privileged to observe the web in its illuminated phase. When galaxies still shine and the structure remains visible through its luminous tracers, we can map the filaments, study the nodes, measure the voids. We can trace the architecture that dark matter built and recognize it for what it is, not an anomaly or a puzzle, but the foundation of everything we see, the scaffolding upon which the visible universe hangs, permanent and essential and profoundly, eternally dark. The scientific method demands skepticism. Every extraordinary claim must be tested, challenged, scrutinized from every angle before acceptance. When observations conflict with established theory, the simplest explanation is not always the correct one. And sometimes the problem lies not with nature, but with our understanding of the laws we thought governed it. Dark matter represented such an extraordinary claim. An invisible substance comprising the majority of the universe's mass. Detectable only through gravity, participating in none of the electromagnetic interactions that define our understanding of matter. It was, by any measure, a radical proposal. And radical proposals invite radical alternatives. Perhaps some physicists suggested the problem was not missing matter, but misunderstood gravity. The idea had a certain appeal. Gravity at cosmic scales, across light years and beyond, had never been tested with the precision achieved in the solar system. Newton's and Einstein's equations worked beautifully for planets orbiting the Sun, for satellites circling Earth, for binary star systems. But galaxies and galaxy clusters operated at vastly different scales, with vastly lower accelerations. Perhaps the laws of gravity, so well verified in strong gravitational fields, behaved differently when the acceleration became extremely small. Modified Newtonian dynamics, or MOND, emerged as the most developed alternative, proposed by physicist Mordechai Milgram in the early 1980s. MOND suggested that at very low accelerations, below a certain threshold, gravity did not decrease with distance, according to Newton's inverse square law, but declined more slowly. This modification would cause objects at the outer edges of galaxies to experience stronger gravitational pull than Newton's law predicted, potentially explaining the flat rotation curves without invoking dark matter. The theory had some successes. It fit the rotation curves of many spiral galaxies remarkably well, often better than simple dark matter models that assumed spherical halos. It made predictions about the relationship between a galaxy's luminosity and its rotation speed that matched observations. For individual galaxies, MOND provided a viable alternative explanation that eliminated the need for invisible mass. But galaxies are not the only gravitational systems in the universe. And as observations extended to larger scales and more complex environments, MOND's explanatory power began to falter. Galaxy clusters posed difficulties. MOND could account for some of the excess gravitational mass inferred from cluster dynamics, but not all of it. Even with modified gravity, clusters appeared to contain more mass than their visible matter could provide. MOND advocates suggested that some ordinary matter, perhaps in the form of dim stars or cold gas, might fill the gap. But observational limits on such matter made this explanation increasingly strained. Gravitational lensing presented another challenge. Lensing measures mass through the bending of light, a phenomenon governed by general relativity rather than Newtonian gravity. While MOND was originally formulated as a modification of Newtonian dynamics, extending it to a fully relativistic theory that could predict lensing effects proved difficult. Some relativistic versions of MOND were developed, but they often required fine-tuning and introduced complications that reduced their theoretical elegance. Still, these challenges were not fatal. Alternative theories often struggle with certain observations while succeeding with others. The ultimate test for any scientific proposal is not whether it explains everything perfectly, but whether it explains the data better than competing theories. MOND remained a viable alternative, at least for some astrophysicists, until a particular observation in 2006 shifted the landscape decisively. The Bullet Cluster is not a single galaxy cluster, but two, caught in the aftermath of a titanic collision. Located roughly 3.7 billion light-years from Earth, the system consists of two massive galaxy clusters that pass through each other at speeds exceeding 1,000,000 miles per hour. The collision was not recent by human standards. It occurred perhaps 150 million years ago, but by cosmic timescales, We are observing the event shortly after impact, with the debris field still clearly separated. What makes the bullet cluster remarkable is the clarity with which different components can be distinguished. Observations across multiple wavelengths optical X-ray and gravitational lensing studies reveal how different types of matter behave during the collision. The galaxies themselves, being mostly empty space punctuated by stars, pass through each other relatively unscathed. Individual stars within galaxies are so far apart that direct collisions are extraordinarily rare. The galaxies emerged from the encounter largely intact, having sailed through the collision zone with minimal interaction. The hot gas that fills the space between galaxies behaved very differently. This intergalactic medium, heated to millions of degrees and glowing brightly in X-rays, comprises the majority of the ordinary matter in galaxy clusters, far more than the stars in all the galaxies combined. Unlike the galaxies, this gas is not transparent to itself. When two vast clouds of hot gas collide, they interact directly, creating friction, pressure, and shock waves. The X-ray observations of the bullet cluster show exactly this. Two distinct clouds of hot gas separated in space mark where the collision occurred and where the gas from each cluster has slowed heated further by the shock of impact and been left behind as the galaxies continue moving apart. The X-ray emission peaks in these regions, showing where the bulk of the ordinary matter now resides. But the mass map tells a different story. Gravitational lensing analysis of the bullet cluster measuring how light from background galaxies is distorted by the cluster's gravitational field reveals where the majority of the mass is actually located, and that location does not coincide with the X-ray emission. The mass peaks are offset from the gas clouds, centered instead on the galaxy concentrations that passed through the collision. The implication is clear. Most of the mass in the bullet cluster is not in the hot gas, despite the gas containing the majority of the ordinary matter. The mass is somewhere else, and that somewhere else is associated with the galaxies but extends far beyond them, moving with them through the collision without slowing down. This separation mass distinct from ordinary matters difficult to explain without dark matter. If the lensing were responding only to ordinary matter, the mass peaks should coincide with the X-ray emission, where most of the baryonic mass is concentrated. But they do not. The mass has continued moving with the galaxies, which themselves contain relatively little of the cluster's total ordinary matter. The natural explanation is that each galaxy cluster contains a massive halo of dark matter, far exceeding the mass of its ordinary matter. During the collision, the dark matter halos, being collisionless and non-interacting except through gravity, pass through each other like the galaxies themselves. The ordinary matter, primarily the hot gas, collided and was slowed, creating the offset between the mass distribution and the baryonic matter distribution. For dark matter theory, the bullet cluster was powerful confirmation. It demonstrated spatial separation between mass and light, showed that the majority of the mass does not interact through electromagnetic forces, and provided direct visual evidence that something non-baryonic dominates the gravitational field of galaxy clusters. For Mond and other modified gravity theories, the bullet cluster posed a severe challenge. Modified gravity theories propose that the gravitational field is simply stronger than Newton predicts at certain scales or in certain regimes. But gravity, whether Newtonian or modified, responds to the distribution of all matter. It cannot create mass peaks that are offset from where the matter actually is. In Mond, the gravitational field should be strongest where the matter is most concentrated. In the bullet cluster, that would be where the hot gas is located, as measured by X-ray emission. But the lensing maps show the gravitational field is strongest where the galaxies are, not where the gas is. The mass and the ordinary matter have been pulled apart in space. This spatial separation is precisely what dark matter theory predicts, and what modified gravity cannot easily accommodate. If gravity is simply behaving differently than expected, it must still respond to the matter that is present. It cannot create gravitational effects in regions where no matter exists. The bullet cluster shows gravitational effects strong enough to create multiple imaged lensing locations offset from the bulk of the baryonic matter. Some modified gravity advocates propose that the missing mass might be ordinary matter in forms not yet detected very cold gas, dim stars, or primordial black holes. But observational constraints on these candidates are stringent. Cold gas would absorb or emit at certain wavelengths. Dim stars would still contribute to the total luminosity. Primordial black holes would produce detectable effects through microlensing or dynamical heating of stellar populations. None of these signatures appear in sufficient quantity to account for the observed mass. Moreover, the amount of ordinary matter is independently constrained by Big Bang nucleosynthesis, the process by which light elements were formed in the first few minutes after the Big Bang. The abundances of hydrogen, deuterium, helium, and lithium that we observe in the universe match predictions only if the total amount of ordinary matter falls within a specific range. That range is far below the total mass implied by gravitational observations. There is simply not enough ordinary matter in the universe to explain the gravitational effects we see, regardless of what form it takes. The bullet cluster became known as the smoking gun for dark matter, not because it was the first evidence or the strongest evidence in isolation, but because it was the clearest visual demonstration of the core prediction that most of the gravitating mass is not ordinary matter and does not interact through electromagnetic forces. Subsequent observations of other colliding galaxy clusters have reinforced this conclusion. The Abel 520 system, the Trainwreck cluster, and others show similar separations between mass and light, though the details vary depending on the geometry and timing of the collision. Each case provides additional confirmation that the majority of the mass in these systems is dark, collisionless, and spatially distinct from the ordinary matter. These observations do not prove that dark matter is composed of particles. They do not reveal what dark matter is made of or how it was produced in the early universe. But they do establish, beyond reasonable doubt, that there is substance present real, gravitating matter that is not interacting electromagnetically and is not composed of ordinary atoms. Modified gravity theories have not disappeared in response to these observations. Science accommodates multiple approaches, and alternative theories continue to be developed and tested. Some versions of modified gravity now incorporate dark matter-like components to explain observations like the bullet cluster, effectively becoming hybrid theories. Others propose more exotic modifications to general relativity that might, under specific conditions, create the observed spatial separations. But these increasingly elaborate modifications have lost the primary advantage that made MOND initially attractive: simplicity. The original appeal of modifying gravity was that it eliminated the need to invoke new, undetected particles. It explained anomalous observations by changing the laws rather than adding new entities. But as observations have accumulated, particularly from colliding clusters, the modified gravity approach has been forced to incorporate additional components, dark fields, additional gravitational degrees of freedom, or even dark matter-like substances under different names to match the data. Dark matter theory, by contrast, has remained relatively simple. It proposes one new ingredient, a type of matter that interacts only through gravity. This single addition explains rotation curves, cluster dynamics, gravitational lensing, the cosmic web, and colliding cluster observations through the same mechanism, the gravitational influence of non-baryonic mass. The theory makes consistent predictions across vastly different scales and environments. The bullet cluster and similar systems demonstrate the limits of trying to explain observations without invoking new forms of matter. The spatial separation of mass and light, the persistence of gravitational effects in regions where ordinary matter is sparse, and the behavior of colliding systems all point to the presence of substance rather than modified laws. Yet even with this evidence, dark matter remains profoundly mysterious. We know it exists. We know roughly how much of it there is. We know how it is distributed on cosmic scales, but we do not know what it is made of. The particles, if they are particles, have never been directly detected. Experiments deep underground, shielded from cosmic rays and designed to catch the rare interactions of dark matter particles with ordinary matter, have been running for decades with ever-increasing sensitivity. So far, no confirmed detection. The dark matter particles, if they exist, interact so rarely and so weakly that even detectors containing tons of target material, monitored for years, have not registered an unambiguous signal. Particle accelerators, including the Large Hadron Collider, have searched for dark matter production in high-energy collisions. If dark matter particles can be created from ordinary matter under the right conditions, they might be produced in these experiments and detected through the missing energy they carry away. Again, no confirmed detection. The experiments have constrained the possible properties of dark matter particles, ruling out certain mass ranges and interaction strengths, but they have not revealed what dark matter actually is. This absence of direct detection is not evidence against dark matter's existence. It is evidence of dark matter's non-interactive nature, the very property that makes it dark. A particle that barely interacts with ordinary matter would be extraordinarily difficult to detect, requiring experiments at the limits of current technology and perhaps beyond. The bullet cluster shows us that this non-interactive substance is real, that it has mass, that it responds to gravity and creates gravitational fields, and that it can be separated spatially from ordinary matter under the right circumstances. It proves that dark matter is not an artifact of modified laws or missing ordinary matter, but a genuine component of cosmic reality. What it cannot tell us is the nature of that component. The lensing maps reveal where the dark matter is and how much there is, but they are silent on what it is made of. The collision dynamics show that dark matter is collisionless, passing through itself and through ordinary matter without significant interaction. But they do not identify the particles or fields responsible. Dark matter remains untouchable in the most literal sense. It cannot be held, heated, or chemically bonded. It passes through matter as if matter were not there. It exists in a realm of physics that remains inaccessible to direct experimentation, revealed only through its gravitational signature, only through its effects on spacetime and on the motion of things we can see. The bullet cluster brought clarity to one question while deepening another. It settled the debate about whether dark matter exists as a substance rather than a modification of gravity. The evidence is now overwhelming that something is there, something with mass, something that dominates the gravitational budget of the universe. But it left untouched the deeper mystery. We have proven that the universe contains substance we cannot perceive, mass that will not shine, matter that inhabits the same space we do while remaining forever separated by its refusal to interact. We have confirmed its presence beyond doubt. We have mapped its distribution across billions of light years. We have watched it pass through collisions, trace the cosmic web, and shape the destiny of galaxies. And still, we do not know what it is. The bullet cluster showed us the shadow, proved the shadow is real, demonstrated that the shadow has weight and consequence. But the substance casting the shadow remains hidden, existing in a parallel realm of physics that touches ours only through the universal language of gravity. The mystery persists not from lack of evidence, but from the profound otherness of what we have discovered, a form of matter so removed from our experience that even confirmation of its existence brings us no closer to understanding its nature. The universe, as it turns out, is mostly made of things we have never touched. This is not poetic exaggeration. It is a precise statement of cosmic accounting, the result of decades of careful observation, measurement, and analysis. When cosmologists add up all the contributions to the universe's total energy density, everything that gravitates, everything that influences the expansion rate, everything that contributes to the curvature of space-time, they arrive at a breakdown that is as humbling as it is precise. Ordinary matter, the stuff of atoms and molecules, the substance of stars and planets and living things, constitutes roughly 5% of the universe's total energy budget. 5%. Everything humans have ever directly observed, measured, or interacted with, every photon captured by every telescope. Every element in the periodic table, every chemical reaction, every biological process represents a 20th of what exists. Dark matter comprises approximately 27%, more than 5 times as much as ordinary matter. This invisible substance, detectable only through gravity, forms the structural framework of the cosmos. It shapes galaxies, binds clusters, traces the cosmic web. It is the majority partner in the matter sector, relegating ordinary matter to minority status. The remaining 68% is something else entirely. Dark energy, a term that labels our ignorance more than our understanding, appears to be a property of space itself. It drives the accelerating expansion of the universe, counteracting gravity on the largest scales, ensuring that distant galaxies recede from us ever faster. Unlike dark matter, which clumps and forms structures, dark energy is smoothly distributed, uniform across space, unchanging with time as far as observations can tell. These percentages, 5, 27, 68, are not rough estimates, subject to wide uncertainty. They are constrained by multiple independent observations: the cosmic microwave background radiation, the large-scale distribution of galaxies, the dynamics of galaxy clusters, the brightness of distant supernova, the patterns of gravitational lensing. Each measurement technique probes the universe in a different way, yet they converge on the same cosmic recipe. The precision is remarkable. The ordinary matter fraction is known to within a few tenths of a percent. The dark matter and dark energy contributions are constrained to within a few percent. This concordance, the fact that such different observations yield consistent answers, gives cosmologists confidence that the model captures something real about the universe's composition. But confidence in the measurements does not diminish the strangeness of the result. 95% of the universe is composed of entities whose fundamental nature remains unknown. Dark matter has never been directly detected in a laboratory. Dark energy has no confirmed theoretical explanation. The vast majority of cosmic reality operates in sectors of physics that remain, at best, poorly understood and, at worst, completely mysterious. For ordinary matter, that 5%, we have a complete inventory. We know it consists of atoms, protons, and neutrons in nuclei, electrons in surrounding clouds. We know protons and neutrons are made of quarks, bound by gluons. We understand the forces governing these particles: electromagnetism, the strong nuclear force, the weak nuclear force. We have a theoretical framework, the standard model of particle physics, that describes their behavior with extraordinary accuracy. This understanding extends to cosmic scales. We know the universe began with hydrogen and helium, synthesized in the first few minutes after the Big Bang. We know heavier elements formed in stars through nuclear fusion, scattered into space by supernova, incorporated into new generations of stars and planets. We can trace the chemical evolution of the cosmos, the gradual enrichment of intergalactic gas with carbon, oxygen, iron, and all the elements necessary for chemistry and life. We know where ordinary matter is located. Most of it resides not in stars, but in diffuse gas, cloud swarm, hot intergalactic medium. Hot gas and galaxy clusters, cool hydrogen clouds along cosmic filaments. Stars contain only a small fraction of the total ordinary matter budget. Planets, asteroids, comets, and all the solid objects we think of as substantial represent an even tinier fraction, perhaps 0.1% of the ordinary matter, which itself is only 5% of the total. Our entire lived experience, every physical object we have ever encountered, every atom in our bodies and our world is drawn from this vanishingly small subset of cosmic reality. Dark matter's 27% is distributed very differently. It does not clump as tightly as ordinary matter because it cannot radiate energy. When ordinary matter falls into a gravitational potential well, it collides, heats up, and radiates that heat away, allowing it to settle into compact configurations like stars and planets. Dark matter, immune to electromagnetic interactions, cannot lose energy this way. It remains diffuse, forming vast halos around galaxies rather than condensing into discrete objects. The dark matter halo surrounding the Milky Way extends perhaps 10 times farther than the visible disk, possibly reaching 200,000 light-years or more from the galactic center. Within this halo, dark matter particles, if they are particles, orbit under the influence of gravity, tracing paths that never bring them into contact with one another or with ordinary matter in any meaningful sense. The density of dark matter in our local neighborhood here in the solar system's region of the galaxy is extraordinarily low by terrestrial standards. Estimates suggest roughly 1 proton mass worth of dark matter per few cubic centimeters. This is far more tenuous than the best vacuum achievable in any laboratory. Yet because dark matter is so abundant on cosmic scales, even this diffuse presence adds up to significant gravitational influence. At any given moment, dark matter particles are passing through your body. Billions of them, perhaps trillions, depending on their mass. They pass through the Earth as if it were empty space, undeflected by the electromagnetic fields that define solidity for ordinary matter. The planet is transparent to them. You are transparent to them. They traverse the solar system, the galaxy, the cosmic web, following gravitational trajectories, indifferent to the existence of atoms and molecules. This indifference is absolute. Dark matter does not feel the electromagnetic force, so it does not interact with photons. It does not participate in the strong nuclear force, so it does not bind into nuclei. It does not engage in the weak nuclear force in any way we have detected. Though some theoretical models suggest weak interactions might occur at rates too low to observe with current experiments, what remains is gravity. Dark matter feels gravity and exerts gravity. This single interaction is sufficient to shape the large-scale structure of the universe, to determine where galaxies form, to hold clusters together, to trace the cosmic web. But it is not sufficient to make dark matter tangible or detectable through any means except its gravitational signature. The leading theoretical framework for dark matter is cold dark matter. The cold referring not to temperature in the conventional sense, but to the particles' velocities. Cold dark matter particles move slowly compared to the speed of light, especially in the early universe when structure formation began. This sluggishness allows them to clump on small scales, forming the halos around individual galaxies rather than only contributing to large-scale structure. Hot dark matter, by contrast, would consist of particles moving at relativistic speeds. Such particles would not settle into galaxy-scale halos, but would only clump on much larger scales. Neutrinos, for instance, are a form of hot dark matter, though they do not constitute the majority of dark matter, because their mass is too small and their velocities too high to explain observed structure. Cold dark matter fits the observations. Simulations that assume cold dark matter particles produce galaxy distributions, rotation curves, and large-scale structure that match what we observe. The halos predicted by these simulations have density profiles consistent with gravitational lensing measurements. The timing of structure formation in cold dark matter models aligns with the age of the oldest galaxies we observe. The most popular candidate for cold dark matter is the WIMP weakly interacting massive particle. These hypothetical particles would have masses perhaps tens or hundreds of times that of a proton and would interact through gravity and possibly through the weak nuclear force, but not through electromagnetism or the strong force. They arise naturally in certain extensions of the standard model of particle physics, particularly in theories involving supersymmetry, which propose that every known particle has a heavier partner particle. WIMPs have the attractive property that their predicted abundance, calculated from the physics of the early universe, matches the observed dark matter density. In the first moments after the Big Bang, when the universe was hot and dense enough, WIMPs would have been in thermal equilibrium with ordinary matter constantly being created and annihilated in particle collisions. As the universe expanded and cooled, the creation process became less efficient, and the WIMPs froze out, leaving behind a relic population whose density depends on how strongly WIMPs interact with other particles. This thermal freeze-out mechanism predicts that particles with weak-scale interactions, roughly the strength of the weak nuclear force, would produce the correct dark matter abundance. The fact that this prediction matches observations without requiring fine-tuning has made WIMPs a leading candidate for decades. Yet, despite extensive searches, WIMPs have not been detected. Underground detectors containing tons of ultra-pure materials, cooled to near absolute zero and shielded from cosmic rays, have been operating for years, waiting for a WIMP to collide with an atomic nucleus and produce a detectable signal. The sensitivity has improved by orders of magnitude. Still, no confirmed detection. This null result does not rule out WIMPs entirely. There is still parameter space where they could be hiding, with masses or interaction strengths just beyond current experimental reach. But it has opened the door to alternative candidates. Ixians, originally proposed to solve a different problem in particle physics, could also serve as dark matter if they exist in sufficient quantities. Sterile neutrinos, hypothetical cousins of the known neutrinos, are another possibility. More exotic proposals include primordial black holes formed in the early universe or entirely new classes of particles with properties unlike anything in the standard model. The identity of dark matter remains one of the deepest open questions in physics. We know how much of it there is. We know how it is distributed. We know it must be cold, collisionless, and stable over billions of years. But the specific particle or particles that constitute it remain elusive. This ignorance is not for lack of effort. Billions of dollars have been invested in dark matter detection experiments. Thousands of physicists have devoted their careers to the search. The particle physics community has made dark matter detection one of its highest priorities, yet the dark matter keeps its secrets, remaining tantalizingly just beyond the threshold of detection. Perhaps the particles are lighter than expected, or heavier, or more weakly interacting, or composed of multiple species rather than a single type. Perhaps direct detection is impossible with any technology we can envision, and dark matter will remain knowable only through its gravitational effects. Perhaps the answer lies in physics we have not yet imagined. Extensions of the standard model that go beyond current theoretical frameworks. What we can say with certainty is that this unknown substance constitutes more than a quarter of everything that exists. It is not a trace contaminant or a minor correction to cosmic inventories. It is a dominant component, more massive than all the stars and all the galaxies combined, more abundant than all the gas clouds and dust lanes and planets, more prevalent than every atom in the periodic table added together. For every kilogram of ordinary matter in the universe, there are roughly 5 kilograms of dark matter. This ratio holds everywhere in galaxy halos, in galaxy clusters averaged across the cosmic web. The dark matter is not confined to distant regions or exotic environments. It is here, around us, passing through us, present in quantities that dwarf the ordinary matter in our immediate vicinity. The Milky Way contains perhaps 1 trillion solar masses of dark matter in its halo, compared to roughly 60 billion solar masses of stars, and perhaps another 20 billion in gas and dust. The dark matter outweighs the visible galaxy by a factor of more than 10. Our solar system orbits not just under the gravitational influence of the galaxy-S stars and gas, but primarily under the pull of the dark matter halo in which everything is embedded. On a more personal scale, the room you occupy right now contains dark matter. Not much. The local density is too low for any measurable amount to be present in a human-sized volume. But integrated over larger scales, over the volume of a building, a city, the Earth, the dark matter mass accumulates. The Earth is constantly moving through the dark matter halo, like a ship through an ocean. Except the ocean does not resist, does not slow the ship, does not even acknowledge that the ship is there. This is the numerical reality of our situation. We live in a universe where 95% of the content is not made of atoms, where the majority of gravitating mass is invisible and intangible, where the framework that determines cosmic structure, scaffolding that allowed galaxies to form and stars to ignite and planets to coalesce, is composed of something we have never held and may never directly detect. Human history, all of science and technology, all of chemistry and biology and medicine, has been the study of 5% of what exists. The periodic table catalogs the building blocks of that 5%. The laws of thermodynamics govern its behavior. The equations of quantum mechanics describe its properties. All of our accumulated knowledge about how matter behaves, how it heats and cools, how it bonds and breaks, how it flows and crystallizes applies only to this minority constituent. The other 95% operates under different rules. Dark matter follows the laws of gravity but ignores almost everything else. Dark energy, whatever it is, behaves unlike any form of matter or energy familiar from terrestrial physics. Together, these unknown components dominate the universe's evolution, determining how fast it expands, how structure forms, what the ultimate fate of cosmic expansion will be. We are, in a very real sense, peripheral to the main story. The universe's composition is not centered on the kinds of matter and energy we understand. We are made of the exception, not the rule. The atoms in our bodies, the chemical processes that sustain life, the electromagnetic interactions that allow us to see and touch and measure the world, all of this unfolds within a narrow sector of reality. While the bulk of existence proceeds according to principles we are only beginning to glimpse. This realization is the culmination of a long process of displacement. Copernicus displaced Earth from the center of the solar system. Hubble displaced our galaxy from the center of the universe. Now cosmology has displaced our very composition from the majority category of cosmic matter. We are not just occupying a random location in space and time. We are made of a random minority type of substance, swimming in an ocean of the unknown. The 5% figure is precise, but its implications are profound. It means that everything we have ever directly studied, every experiment conducted, every observation made through microscopes and telescopes and particle detectors has explored only a small corner of physical reality. The rest remains hidden, not because it is far away or difficult to access, but because it simply does not interact with the tools and methods we have developed. Dark matter surrounds us, permeates us, outweighs us by a factor of 5, and yet it remains as remote and inaccessible as if it occupied a different universe entirely. We share the same space, move through the same gravitational fields, but we are fundamentally separated by the absence of interaction. The dark matter is indifferent to our presence. It does not notice when we build cities or launch spacecraft. It does not respond to our attempts to capture it in detectors. It exists in parallel, a ghost universe occupying the same location but forever unreachable. This is the percentage of reality. 5% known, 27% dark matter, 68% dark energy. The numbers are precise. The mystery is complete, and we continue, as we must, trying to understand the 95% that remains beyond our grasp, armed only with gravity as our guide and a conviction that the universe, however strange, is ultimately comprehensible. The universe will not end in fire. The evidence accumulated over the past few decades points to a different conclusion, one slower and quieter, a gradual dissolution rather than a catastrophic finale. The galaxies will not collapse back into a singular point. The stars will not reignite in a final blaze. Instead, the cosmos will expand forever, diluting itself across ever greater volumes, cooling and darkening until nothing remains but cold, isolated remnants scattered across an unimaginable void. This fate was not always inevitable. For most of the 20th century, cosmologists debated whether the universe contained enough matter to halt its expansion and reverse it, pulling everything back together in a big crunch, or whether the expansion would continue forever, gradually slowing but never quite stopping. The answer depended on the total density of matter and energy, a critical parameter that observations were slowly constraining. The discovery that changed everything came at the turn of the millennium. Observations of distant supernovae exploding stars whose brightness could be used as standard candles to measure cosmic distances revealed that the universe's expansion was not slowing at all. It was accelerating. Galaxies far away were receding faster than they should if gravity were the only significant force at work. This acceleration implied the existence of something with repulsive gravitational properties, something that pushed rather than pulled on cosmic scales. Dark energy was the name given to this entity, though the name, like dark matter, was more a placeholder than an explanation. Whatever dark energy is, it comprises roughly 68% of the universe's total energy budget, and its influence becomes dominant at large scales where matter, both ordinary and dark, is too diffuse to counteract it. The presence of dark energy determines the universe's ultimate trajectory. Rather than expansion slowing asymptotically toward zero, the expansion rate will remain positive, possibly even increasing over time if dark energy's properties remain constant or strengthen. The space between galaxy clusters will continue growing. The cosmic web, held together by dark matter's gravitational influence, will stretch and thin. Eventually, the filaments will become so attenuated that they lose their structural coherence, and the nodes, the galaxy clusters, will become isolated islands in an ever-expanding ocean of space. On timescales of trillions of years, the effects will become profound. Galaxies within gravitationally bound groups will merge, their stars mingling, their dark matter halos coalescing. The Milky Way and Andromeda are already on a collision course, destined to merge in perhaps 4 billion years. Other members of our local group will eventually be incorporated as well, forming a single, massive elliptical galaxy surrounded by a unified dark matter halo. But this merged galaxy will be alone. The accelerating expansion will have carried other galaxy groups beyond the reach of gravitational binding. Light from these distant systems will be redshifted to longer and longer wavelengths, eventually stretching beyond the visible spectrum, beyond infrared, beyond radio waves, becoming undetectable. The observable universe will shrink, not because space is contracting, but because the expansion carries distant objects past the point where their light can reach us. Observers in this far future, any exist, will look out at a sky nearly empty of galaxies. The cosmic web will be invisible, its structure erased by distance and expansion. The cosmic microwave background, already faint today, will be redshifted into oblivion. Its photons stretch to wavelengths so long they become indistinguishable from the vacuum. Future cosmologists will have no direct evidence that the universe was once denser, hotter, or more richly populated with galaxies. They will inhabit an island universe, a single merged galaxy surrounded by darkness. If they attempt to reconstruct cosmic history from local evidence alone, they may conclude that their galaxy is the entirety of the universe, that nothing exists beyond it, that the cosmos has always been a single structure in an infinite void. They will have lost the perspective that our current epoch provides: the ability to see the cosmic web, to observe distant galaxies, to map the large-scale structure that reveals the universe's true nature. Within the island galaxy itself, the story will be one of gradual exhaustion. Star formation requires gas, and the supply of gas is finite. The interstellar medium will slowly be converted into stars, and those stars will burn through their fuel and die, returning some material to the interstellar medium, but locking much of it into stellar remnants, white dwarfs, neutron stars, black holes. The rate of star formation will decline. The galaxy will redden as the massive bright blue stars die off and only the longer-lived red dwarfs remain. Eventually, even the red dwarfs will exhaust their hydrogen fuel. The last stars will flicker out perhaps 10 trillion years from now, leaving behind a galaxy of cold stellar corpses and planets orbiting in the dark. The dark matter halo will remain. Unlike ordinary matter, Dark matter does not radiate energy or condense into compact objects. It will continue orbiting under gravity's influence, tracing elliptical paths through the merged galaxy's gravitational potential. Indifferent to the fate of the luminous matter it once helped organize. But even the dark matter structure will not last forever. Gravitational interactions between stellar remnants and dark matter particles will slowly transfer energy, a process called dynamical relaxation. Over inconceivable timescales, perhaps a Google years. 10 to the 100th power, this process could evaporate the dark matter halo, ejecting particles to infinite distances. The galaxy's visible remnants might collapse into a supermassive black hole, or they might disperse entirely, depending on the detailed dynamics of this slow gravitational evolution. Black holes themselves are not eternal. Stephen Hawking showed that black holes emit radiation through quantum processes at their event horizons, slowly losing mass over time. A solar mass black hole would take longer than the current age of the universe raised to an enormous power to evaporate, but given infinite time, even the largest black holes will eventually decay, releasing their mass energy back into the void as a faint hiss of particles and radiation. In the ultimate future, the universe will contain only isolated particles, photons stretched to infinite wavelength, neutrinos flying through empty space, perhaps dark matter particles still obeying gravity's pull, but with nothing left to pull on. The temperature will asymptotically approach absolute zero. Entropy will reach its maximum. Nothing will change. Nothing will happen. The universe will be dead, not from collapse, but from diffusion. Its energy spreads so thinly that no local concentration remains sufficient to power any process. This heat-death scenario assumes that dark energy remains constant, a cosmological constant in Einstein's equations unchanging over time. But dark energy's nature is even more mysterious than dark matter's. If dark energy strengthens over time, a possibility, some theoretical models allow the fate could be more dramatic. In a scenario called the Big Rip, dark energy's repulsive effect would grow strong enough to overcome not just the gravitational binding of galaxy clusters, but eventually galaxies themselves, then solar systems, then planets, then molecules, then atoms. The fabric of space-time would expand so violently that every bound structure would be torn apart, right down to the subatomic level. This would occur not in the infinite future, but at a specific moment, perhaps tens of billions of years from now. Current observations constrain how dark energy can evolve, and nothing yet suggests the Big Rip is likely. But the possibility exists, a reminder that the universe's ultimate fate depends on physics we do not yet fully understand. Dark energy could decay, transforming into something else. It could oscillate, driving cycles of acceleration and deceleration. It could be a temporary phase, not a permanent feature. We observe its effects today, but we cannot predict with certainty what it will do tomorrow, cosmologically speaking. What seems certain is that the era of abundant light and nearby galaxies is temporary. We live in a cosmological moment when the universe is old enough to have formed complex structures, but young enough that those structures remain visible and accessible. The cosmic web spans the sky. The cosmic microwave background carries information from the early universe. Distant galaxies show us cosmic history, their light having traveled for billions of years to reach us. This richness will not last. The accelerating expansion is already beginning to limit what future observers will see. Galaxies at the edge of the observable universe today will eventually recede beyond the cosmic horizon. Their light redshifted so severely that it can never reach us, no matter how long we wait. The information they carry about distant regions of space will be lost, not destroyed, but rendered permanently inaccessible. Dark matter's role in this unfolding story is as structural backbone and ultimately as survivor. The dark matter halos that hold galaxies together will persist long after the stars have died. They will continue to trace gravitational potential wells even when nothing luminous remains to mark their locations. In the far future, when all ordinary matter has either collapsed into black holes or been ejected into the void. The dark matter will still be there, invisible as ever, orbiting through space according to gravity's dictates. But before the universe reaches this terminal state, before the last stars fade and the cosmic web dissolves, humanity has one remaining ambition: to detect dark matter directly, to capture a single particle in a detector and prove beyond any doubt that this invisible ocean is made of discrete entities obeying quantum mechanical laws. The search continues in deep underground laboratories, shielded from cosmic rays by kilometers of rock. Detectors filled with liquid xenon or germanium crystals sit in near-perfect darkness, cooled to temperatures just above absolute zero, waiting for a dark matter particle to collide with an atomic nucleus and produce a tiny flash of light or a minuscule energy deposit. The sensitivity increases with each new generation of experiments, probing smaller interaction strengths and a wider range of possible particle masses. Other searches look for dark matter, annihilation, or decay, processes that might produce detectable particles or radiation. Space-based telescopes scan the galaxy's center and nearby dwarf galaxies, looking for excess gamma rays that could signal dark matter particles destroying each other. The signals must be distinguished from astrophysical backgrounds, pulsars, supernova remnants, cosmic ray interactions, a challenging task that requires careful modeling and statistical analysis. Particle accelerators attempt to create dark matter in collisions between ordinary particles. If dark matter particles can be produced at energies achievable by current machines, they would reveal themselves through missing energy and momentum in collision event signatures that something was created but escaped the detector without interacting. So far, the searches have yielded only constraints: upper limits on how strongly dark matter can interact, but no definitive signal. The absence of detection does not diminish the certainty that dark matter exists. The gravitational evidence is overwhelming and consistent. But direct detection would open new avenues of investigation. It would allow measurement of dark matter's particle properties, mass interaction, cross-section, possibly spin, and other quantum numbers. It would connect the cosmological evidence with laboratory physics, bridging the gap between astronomical observations and particle theory. Such a detection would represent a profound moment in the history of science, the first time humanity directly touched a component of the cosmos that has remained invisible throughout our entire evolutionary and technological development. It would be evidence that the universe's hidden majority is not forever beyond reach. That patient effort and advancing technology can eventually illuminate even the darkest corners of physical reality. But the search is difficult, and success is not guaranteed. The particles may interact too weakly for current detectors to register. They may have properties that place them outside the parameter space our experiments can probe. The answer might require technologies we have not yet invented or theoretical insights we have not yet achieved. Meanwhile, the universe continues its inexorable expansion. Dark energy pushes the cosmic web apart. Galaxies drift toward isolation. The window of opportunity for understanding the full cosmos, seeing the large-scale structure, measuring the cosmic microwave background, observing distant galaxies slowly closing, not in human lifetimes or even in the lifetime of our species, but on cosmic timescales. The era of rich observational cosmology is a brief moment. We are fortunate to live when we do, when the evidence of the Big Bang and the cosmic web and dark matter's influence is still accessible. Future civilizations, if they arise billions of years from now, will face a darker, emptier sky. They may never know that the universe was once filled with galaxies, that matter once formed a cosmic web, that the expansion is accelerating. They will have lost the information we currently possess, not through any failure of observation, but through the relentless progress of cosmic evolution. The dark matter will still be there, surrounding them, pervading their galaxy, dominating the gravitational field. But they may never know it exists. Without the cosmic Web 2 map, without distant galaxies to weigh, without the full richness of cosmological evidence, they might conclude that gravity behaves. As Newton and Einstein predicted, unaware that most of the mass pulling on their stars is invisible. This perspective that our current era is privileged in its observational richness adds urgency to the scientific enterprise. The universe is offering us a temporary glimpse of its full structure and history. The evidence will not remain accessible forever. Dark energy is already erasing information, carrying galaxies beyond our reach, thinning the cosmic web toward invisibility. We stand at a moment when the universe is comprehensible, when enough time has passed for complex structures to form, but not so much time that those structures have dispersed beyond detection. The dark matter scaffolding is still traceable through its gravitational effects. The cosmic microwave background still carries signals from the early universe. Distant galaxies still show us cosmic history. This moment will pass. The light will fade. The structures will dissolve. The universe will return to the darkness from which it briefly emerged, a temporary flowering of complexity in an eternal void. And the dark matter, patient and unchanging, will remain, tracing gravitational paths through empty space. The last remnant of an era when the cosmos was bright enough to illuminate its own mysteries, if only we were patient enough to look. There is something remarkable about a species that can discover its own insignificance and call it progress. We began this journey with confidence in our senses, trust in our instruments, belief that the universe would yield to observation. We charted stars, measured distances, cataloged galaxies. We assumed that to see was to know, that light carried the complete message of cosmic reality. The visible universe seemed vast enough, mysterious enough, to occupy our attention for generations. Then we discovered we had been studying the margins. The rotation curves refused to make sense. The galaxy clusters moved too quickly. The gravitational lensing revealed mass where nothing glowed. Slowly, reluctantly, we were forced to acknowledge that most of the universe's matter was invisible to us, operating in a sector of physics we could only infer through its gravitational signature. Dark matter emerged not as a hypothesis we wanted, but as a conclusion we could not escape. The evidence accumulated from independent observations, each measuring the same deficit in different ways, each pointing to the same extraordinary claim. The universe is dominated by substance we cannot see, touch, or directly detect. This realization could have been demoralizing. We had spent centuries developing increasingly sophisticated tools to observe the cosmos, only to discover that our most powerful telescopes, our most sensitive detectors, our entire electromagnetic toolkit could only access a small fraction of what exists. 95% of the universe's content operates beyond the reach of our observational capabilities. But the response was not despair. It was curiosity. Scientists did not abandon the question when dark matter proved elusive. They refined their measurements, developed new techniques, built experiments to probe ever more subtle interactions. They accepted that the universe did not owe them visibility. That reality could be structured in ways that made it fundamentally difficult to observe. And they adapted their methods accordingly. Gravitational lensing allowed the mapping of invisible mass through its effects on space-time curvature. Computer simulations traced how dark matter and ordinary matter evolved together from the early universe to the present day. Particle physicists proposed candidates for dark matter particles and designed experiments to search for them, even knowing the search might take decades or yield null results. This persistence reflects something essential about scientific inquiry. The goal is not to confirm what we already believe or to discover only what is easily accessible. The goal is to understand reality as it actually is, regardless of how strange or counterintuitive that reality turns out to be. Dark matter forced a humbling adjustment in perspective. We are not the standard composition of the cosmos. The atoms that make up our bodies, our planet. Our stars are the minority constituent, the trace element in a universe built primarily from something else. Everything we have ever directly studied represents only 5% of what exists. Yet that 5% developed the capacity to wonder about the other 95%. This is not a small achievement. The ordinary matter, through billions of years of gravitational collapse and stellar nucleosynthesis, through planetary formation and biological evolution, produced structures capable of asking why galaxies rotate too quickly and what holds clusters together. The minority constituent became conscious, developed mathematics and physics, built telescopes and particle detectors, and turned its attention to the invisible majority. We are, in a sense, the universe studying itself. But more precisely, we are one small part of the universe, the luminous, electromagnetically active parts, studying the much larger dark component that provided the gravitational framework for our existence. The dark matter allowed us to exist. Without it, structure formation would have proceeded too slowly. Galaxies would not have assembled when they did. The gravitational potential wells that gathered gas into star-forming regions would have been absent or weak. The cosmic web, which channeled matter into the configurations that became galaxies, would not have formed. We owe our existence to the invisible scaffolding. The dark matter was here first, creating the architecture within which ordinary matter could organize itself into stars and planets, and eventually, living things. We are latecomers to a universe that was always dominated by the dark. And now, having discovered this, we are trying to understand it. The search for dark matter particles continues in laboratories around the world. Deep underground, shielded from cosmic ray interference, detectors wait for the rare collision that would signal a dark matter particle passing through ordinary matter. The experiments grow more sensitive with each generation, probing parameter space that was inaccessible to earlier technology. The lack of detection so far has not discouraged the effort. It has refined it. Each null result constrains the possible properties of dark matter, ruling out certain mass ranges and interaction strengths, narrowing the search space. The experiments will continue, growing larger and more sensitive, until either dark matter is directly detected or the parameter space becomes so constrained that new theoretical approaches are required. This is patient work, the kind that may take generations to bear fruit. It requires building detectors that can register signals smaller than background noise, distinguishing genuine interactions from random fluctuations, collaborating across international teams to pool data and expertise. It is science at its most careful and methodical, pursuing a goal that may always remain just beyond reach. But the pursuit itself is meaningful. Whether or not dark matter particles are ever directly detected, the effort to understand them represents humanity at its best, curious, persistent, willing to confront the limits of knowledge and push against them. We are a species that looks up at the night sky and asks questions. What are those points of light? How far away are they? What are they made of? How did they form? These questions have driven centuries of astronomical observation, each answer revealing new questions, each discovery expanding the scope of what we know and what we know we do not know. Dark matter is the latest, and perhaps the most profound, question in this long sequence. It asks us to accept that the universe contains more than our senses suggest. That reality extends beyond the electromagnetic spectrum, that most of what exists is fundamentally different from what we are made of. And we have accepted it. Not icily, not without skepticism and rigorous testing, but we have followed the evidence to its conclusion. The dark matter is real. It dominates the cosmos. It shapes the destiny of galaxies and the structure of the universe itself. This acceptance is a triumph of intellectual honesty over anthropocentric comfort. It would have been easier to dismiss the anomalies, to assume the measurements were wrong, to modify gravity in arbitrary ways to avoid invoking new entities. But the evidence became too strong, too consistent across too many independent observations. The universe was telling us something about its composition, and we listened. We are the quiet spectators of a universe that was never designed for our comprehension. Evolution shaped our senses to navigate a specific environment to planet's surface, illuminated by a star, governed by moderate temperatures and pressures. We see the wavelengths reflected by vegetation and skin. We hear the frequencies that travel through air. We feel the textures and temperatures relevant to survival. None of this prepared us to understand quantum mechanics or general relativity or dark matter. These domains of reality operate at scales and in ways that have no overlap with our evolutionary history. Yet we have managed, through the disciplined application of reason and the careful accumulation of evidence, to extend our understanding far beyond what our biology equipped us for. Mathematics became the language through which we could describe what we could not directly perceive. Instruments extended our senses into wavelengths and scales inaccessible to unaided human observation. Theoretical frameworks allowed us to organize observations into coherent models, predicting new phenomena and testing those predictions against reality. Dark matter exists at the intersection of observation and theory. We cannot see it, but we can see its effects. We cannot touch it, but we can measure its gravitational influence. We cannot bring it into a laboratory, but we can model its behavior and test those models against cosmic structure. This indirect approach is not a limitation, but a demonstration of how far human curiosity can reach. We have learned to read the shadows, to infer the presence of objects from the distortions they create, to build a picture of reality that includes components we may never directly access. The journey has been long. From Zwicky's early observations in the 1930s, through Rubin's rotation curve measurements in the 1970s, to the modern era of gravitational lensing and large-scale structure surveys, the evidence has accumulated steadily. Each generation of scientists built on the work of previous generations, refining measurements, developing new techniques, gradually constructing a picture of a universe dominated by the invisible. We now know that dark matter forms halos around galaxies, pervades galaxy clusters, traces the cosmic web across billions of light-years. We know it is cold, collisionless, stable over cosmological timescales. We know how much of it there is and how it is distributed. We know it played a crucial role in structure formation and continues to shape cosmic evolution. What we do not know is what it is made of. This gap in our knowledge is profound, but it is not a failure. It is a frontier. The identity of dark matter particles, if they are particles, remains one of the great open questions in physics, driving experimental programs and theoretical research around the world. The search may take decades more. It may require technologies we have not yet invented or insights we have not yet achieved. Or it may succeed tomorrow with a single, unmistakable signal in a detector somewhere. A dark matter particle finally making its presence known through a rare interaction with ordinary matter. Either way, the question is worth pursuing. Understanding dark matter would complete our picture of cosmic composition, connecting the gravitational evidence from astronomy with the particle physics that describes matter's fundamental nature. It would open new windows into the early universe, when dark matter and ordinary matter existed in different proportions and different states. It would reveal new physics beyond the standard model, expanding our knowledge of what kinds of particles can exist and how they behave. But even if dark matter's identity remains forever mysterious, even if direct detection proves impossible, the journey itself has been worthwhile. We have learned that the universe is stranger and richer than we imagined. We have discovered that most of what exists is invisible to us, yet we have found ways to map it, measure it, and incorporate it into our models of cosmic evolution. This is the power of science, not to provide easy answers or comfortable conclusions, but to pursue truth wherever it leads, to accept reality on its own terms, to build understanding incrementally through observation and reasoning. We are made of atoms, the minority constituent of cosmic matter. We are temporary structures, patterns of ordinary matter that persist for a few decades before dissolving back into the environment. We inhabit a planet orbiting an ordinary star in an ordinary galaxy, located at no special position in the universe, composed of no special material. And yet we are the part of the universe that has developed eyes to wonder about the dark. This capacity for wonder, for asking questions that extend far beyond immediate survival needs, is perhaps the most remarkable feature of human consciousness. We do not need to understand dark matter to survive. It does not affect our daily lives in any direct way. The dark matter particles passing through us at every moment have no measurable impact on our biology or our environment. But we ask anyway. We want to know. We build experiments and telescopes. We develop theories and simulations. We dedicate careers and resources to understanding something that will never be seen or touched, simply because it is there and we are curious. This curiosity is our gift and our burden. It drives us to explore, to question, to push against the boundaries of knowledge. It has taken us from wondering about the stars to mapping the cosmic web. From cataloging visible light to inferring the presence of invisible matter, from measuring our local environment to reconstructing the history of the universe. The journey has revealed our smallness. We are 5% of the matter, occupying one moment in cosmic history, observing from one location in an unremarkable galaxy. The universe does not revolve around us, does not conform to our intuitions. It is vastly larger, older, and more complex than our ancestors imagined. But the journey has also revealed our capability. We have learned to see past our limitations, to construct knowledge from fragments of evidence, to build models that predict observations we have not yet made. We have discovered that curiosity and reason, applied patiently over generations, can illuminate even the darkest mysteries. Dark matter remains mysterious, but it is no longer unknown. We have brought it from speculation to established science, from an ad hoc hypothesis to a central component of cosmological models. We have mapped its distribution, constrained its properties, incorporated it into our understanding of how the universe formed and evolved. The work continues. The detectors run. The telescopes observe. The theorists calculate. The search for understanding persists, driven by the simple recognition that the universe contains mysteries worth pursuing, and that we, improbable as it seems, have the capacity to pursue them. We are the quiet spectators, watching a universe that was here long before us and will remain long after we are gone. We occupy a brief moment when the cosmos is observable, when the evidence of its history and composition is still accessible, when the questions can still be asked and answered. We are made of the light, studying the dark. We are the minority wondering about the majority. We are 5% trying to understand the other 95%. And in that effort, in the patient accumulation of evidence and the disciplined pursuit of truth, we find meaning. Not because the universe was made for us or because we are central to its story, but because we are capable of asking the questions and willing to accept the answers, however humbling they may be. The screen fades to darkness, but the darkness is no longer empty. It is filled with matter we cannot see, particles we have not yet identified, structures we are still learning to map. It is the majority of what exists, the foundation of cosmic architecture, the invisible ocean in which we swim. And somewhere in that darkness we continue searching, driven by curiosity, guided by evidence, content to be small in a universe that is vast, temporary, in a cosmos that is eternal, ordinary matter in a reality dominated by the dark. The journey has only just begun.